Hello all, welcome to the TwistedBox Jewelry webinar for Morphine Streams 2.0. My name is Michael Pryor, Design Director of Design Morphine and Computational Designer at Nike. This webinar is going to focus on using twisted boxes, primarily coming from Pufferfish, along with other supporting plugins to create the idea of jewelry, but also could be applied to other types of systems or surfaces or meshes. And so, just as an intro, to get Pufferfish, you just go to Food for Rhino, and same to get the other plugins, except for Weaverbird. And so if we just go to Food for Rhino's homepage, you can find Pufferfish here, and it works for Rhino 5, 6, Mac, and 7 work in progress. So Pufferfish is a plugin that it's mainly focused on tweens, blends, morphs, averages, transformations, and interpolations, which is essentially shape changing. It currently consists of 305 components and will be growing soon. It has a lot of really good contributors, whether directly or indirectly, which you can see here, who everyone that has in some way contributed to the plugin is credited here. And if you want to keep up to date with Pufferfish, you should follow me on my Instagram at ecom.royup, or also at Design Morphine if you're not following already. So if I go down here, you'll want to download, we'll be using Pufferfish 2.8, and make sure that you also download the 2.8 examples, which has an example file for every component in Pufferfish, as well as workflow examples, which are showing more kind of overall examples and systems. So if you get stuck on a component or want to know what someone's doing, please download those, and it should get you through what you're trying to understand with a specific component with Pufferfish. So I'll go now to Rhino. So Pufferfish here consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 tabs currently. They're separated as color, curve, domain, list, mesh, number, plane, point, sub D, which will only work in Rhino 7 work in progress. They'll still be here if you're using Rhino 5 or 6, but the components won't actually work. They'll throw errors if you put them on the canvas like that, right? Because I'm in Rhino 6 right now. And surface, transform, twisted box, which we'll be focusing mostly on in this webinar, and vector. Now, the Pufferfish has basically 4 main types of components. They are the tween components, the average, both weighted and regular, and parameter components, as well as twisted box components. Along with those are a lot of support components, which ease the use of these components, or is a lot of the methods that are built in these components kind of deconstructed out. And for instance, like for curve, you have things like aligning curves, compatibilizing polylines. So it's just kind of like support. Everything else is support for that. And then there's other components too, which are just things that I was interested in at the time, such as mirror cut mesh, which we'll use in a part of this tutorial, I think. And like discrete polyline, stuff like that. So sometimes it's just things I was interested in at the moment. Now, all these, the tweens and average and parameter are existing for each geometry type. So you can see for mesh, there's the tweens and averages. For planes, there's tweens and averages. Surfaces, tweens and averages. And for the most part, they're consistent in their options across, but each geometry type, they have little tweaks and little differences in the way, in the options that they have. The other things, the other thing to note is that there's generally 3 different types of tweens. There's tween 2, tween consecutive, and tween through, and we'll talk about what those mean. And those exist also for twisted boxes as well, like twisted box, 2, through, and consecutive, and then with different geometry types. And the other important thing to know about Pufferfish is all the components are either using factors or parameters, which instead of Grasshopper's usual way, which is by division count. And this allows us to make spacing and division variable by using different kinds of lists and graph mappers. And I think it's one of the first plugins to kind of shift away from division counts. And that was kind of my overall idea when making Pufferfish, is that I wanted access to the parameters. So I have this file here with just some things. For the rest of the webinar after this part, we'll be building definitions and together and doing things in Rhino together manually. But for this part, I just have some things set out that I wanted to talk about to explain what the difference of some of these things are, for instance, like to and through and consecutive, and I find it best to explain what those are by using curves. So this one here, between 2 curves, so what that means is pretty self-explanatory. It's that you're tweening, just going to turn off the previews of other stuff here. Okay, so it just means that you have 2 curves and you're tweening. You're just tweening between them, right? Creating a blend. So what you do there is you have a range here and a number, so and a amount of steps, and so you have all these numbers, and you can get all these blends between, which would be an equal division. It would just be like Rhino's tween. And if we look at it, it's going to be 0 to 1 in this case. Right? So curve A, curve B. So you might notice that Grasshopper also has a tween curves component, which is just called tween curve, right? And you'll see this here, and the results are the same in this case. So why did I first and foremost remake that component? Well, there's just some differences there that I wanted, and there's some weird things with this component that I didn't like. The first thing is the refit and point sample options, which if I bake these curves real quick here, if you ran these curves through Rhino's tween curves, you get division count again. We don't want division count, but you also have match method, right? And there's none, which is my component's default, refit, and sample points. Okay, so those are important in some instances. A refit will rebuild the curves basically by curvature, so you'll have more control points per curvature. And point sample, you equally divide a curve and rebuild the curve, right? So it's just different ways to tween. So if we look at the control points here, okay, and we look at our control points of this one, of our inputs too, right? We don't generate more control points, right? The idea is that you want to have the little amount of control points possible, but stay very accurate. So I'm also using like NURBS math in there with not vectors and weights and those things that are, you know, you should be concerned about, and look at. So if I refit these, and you will refit them to a degree, curve degree, right? So it's refitting these, but we're not outputting those right now, so that's why you don't see them, but see the division of those, right? It gets built by the curvature. Or you can, instead of refitting, you can do a point sample, and that will just be like the number of points, right? So you can see how the number of points, so that green curve, right? So it would change the way that that thing blends, okay? Now the thing that I don't like about the native tween curve is primarily with polylines. If I draw a polyline here and a polyline here, and I'll just set those in, right? So you'll see the green curve, that's Pufferfish's curve. It's pretty accurate to what it should be, right? But for some reason, the Grasshopper one, native one, it gets these weird extra segments and kinks, which just seems incorrect to me. Which I think you just wouldn't want that, right? That's kind of like what you would want there, this kind of blending. Even if there's different amounts of control points, it's better than this kind of like weird thing that has this kind of, I don't know, these kind of tapers almost. So yeah, so by using factors, so just turn this on again. And I actually want to get my original curves back here, okay, which I had internalized. There, okay. So just preview that off, okay. So again, by using a range, you can do something like that, but then you can also use graphs. So if I change this graph type to be Bezier, right? So now I can change the spacing of that and the distribution. And if you did something like a sine wave, you'll see things go like out of order, right? Because your factors are coming back on themselves. So if I did like list item, you'll see that they're not in order, right? Because your sine waves are coming back on each other. So there's a handy component in Pufferfish, which is called linearize numbers, which will take your nonlinear waves and linearize them. So if we bump this up, you can really see it. So you see how the spacing now has a sine wave spacing, but everything is still in order. See? Okay. So that's just an example of one of the like support components that can do some other function like that. So then we can look at the kind of like the accuracy of the tweens in Pufferfish and the, you know, what I was after when making this. If we look at a common way that people might also try to blend curves, would be to divide the curve make lines across and then evaluate those lines and create a new interpolated curve. But the problem with that is that it's not really accurate. So if I bring this curve like to the end, oops, wanted to use the factor here. If I bring it to the end here, I need a lot of points to get accurate to the geometry there. Whereas if I wanted the true amount of points, which is something like, I don't know, 6 or however many, I think it doesn't have many points. There should be like 5 points, so 5. So you see how off, it's very off, that curve from the input. Whereas the pufferfish one here in green is exactly on the input curve, right? So if I just turn this off here, right? So it's exactly, when I go to 0, it's exactly on the input curve. And if I go to 1, it's exactly on the input curve. So it's all about the accuracy. And also, if we look at the control points, which is here, it doesn't gain a ton of control points, right? It's using the correct amount of control points. So that's tween 2, right? You go from one to the other, simple as that. So tween consecutive. Tween consecutive, if I just turn this on, turn on our inputs, okay? So tween consecutive, basically you have, in this case, 3 inputs. I just unpreview that. You have 3 inputs, 1, 2, 3. You can have as many as you want, doesn't matter. And your factor is going to be, whatever your factor is, how many you have, it's going to be between each consecutive pair. Right? So I'll just bring this, if I use one factor, right, so you'll see I'm just using one factor and it's sliding from 0 to 1 and then 1 to 2. So it's, that's what consecutive means. It means whatever factor you use, it's going to put it between both of those. And you can also use a range there. The issue with range is that you're creating a 0 and a 1, and what that's going to do is in the middle here, it's going to create an overlap because it's going to be 0 to 1 and then 0 to 1. So this curve in the middle is going to have factor 1 from this set, and then it's going to have factor 0 from this set. So there's another component in Pufferfish called a reparameterized range, so we can use that instead. And it has an I option, which is include, which says include 0 and 1 in the range, which you can turn to false. So it'll redistribute, it'll have the same amount of factors, but it'll redistribute it so there's no 0 to 1, and then you won't have that overlap in the middle anymore. And the nice thing, once you start to use more than 2 curves, is that you have interpolation types here. And right now it's linear, right? We always have these kind of linear tweens. But this will also let you do different kind of like rounded tweens. In this case, they're straight, normal, tight, uniform. And you can see that it's rounding off there, right? So instead of a linear tween, you can do a rounded tween. And again, for these reparameterized range, you can use the same kind of things. So you can use graphs or whatever. So consecutive means consecutively between each set in the input list. And then there's tween through. So tween through, what that means, if I get just the factor here, one factor, it means that whatever your inputs, we have the same inputs here, the same 3 inputs, but we're going to be able to tween through all of them. from, and it's going past it because we're going past 1. So we'll just make that 1 in this case. So 0, and then 0.5 would be the middle curve. And it doesn't matter where, it's not halfway through, it's wherever the middle curve is in this case. And again, I'm just using 3 here, you can use as many as you want. And then 1, okay? So, if I'll actually just respace these real quick, just so I can show an example. And I'll reset these in. And you want to set your curves and set things in Grasshopper from the parameter first. Otherwise, if you select here first and then set multiple, it's going to set them in the order that they were drawn in Rhino, which is not what we want. We want the order that we select them. So you select the curve, right click, set multiple curves, and just set them in. So the reason I did that was just to change the spacing so that it's closer here and then further there, just to show you that now if I go to 0.5, it's going to be that middle curve still. And when we use a range there, what's going to happen is it's going to be, I'll bring it even closer. So it's going to be tighter in this area here because it's closer. So you see how tight it is there, and then it's going to like loosen up there. So there's an override in the component which is called equalize, and if you equalize, it will redistribute the spacing so that it's nice and equal throughout, no matter the spacing of these, but still keeping the geometry. Now when something's equalized, 0.5 won't be the middle curve. 0.5 would be 0.5 of the overall tween, which happens to be there. Okay, so now you see it's not on that curve anymore, versus if I turn it off, now it is on that curve. So that's another option, which is equalize. Normalized just means 0 to 1 or 0 to the last index of the curve. So right now it's default true, 0 to 1. So if I bring this back in and I turn equalize off just so we can see, so 0, I turned that off, I'm sorry. So 0, 0.5, 1. But if I turn this off, you'll see it's 0, 1, and that's because it's going to the index. So it's just another way to do it if you wanted to. In this case, we have 3 curves, so it'd be 0, 1, 2, right? So the index would go 0, 1, 2. But for the most part, I keep it on and just stick with 0 to 1. Really depends. Just another option there. And we have the different interpolation types, so I'll put my range in here. And just like before, we have linear interpolation and then different curve type interpolations. And we also have here rebuild and point sample. I actually had something for some reason I have that in there, point sample, but I shouldn't have. And you see it was a little bit off because I was redividing by 10, so you see it's a little bit off down there. We don't need the point sample in that case, so we'll just be exact like that. You can turn the equalized off. You can see it's unequal. Turn it on, equal. So the reason that I show all this is because these options are consistent throughout Pufferfish, including in the twisted boxes as well. So if I go to Pufferfish, you can see like between 2 curves, between 2 surface, TwistedBox 2 curves, TwistedBox 2 surface. So they're the same kind of options exist consistently, So you have, again, like RP. This has UVW because, as we'll see later on, twist boxes have a U and V and W space, A, B, or tween through, let's see, twisted box through surfaces, right? So again, you have that normalized, equalized, there's a weighted here, you have the interpolation, right? So those options remain consistent throughout. So if like I went to plane, I went to tween consecutive planes, right? You have the factor, in this case you have a weight and a degree, but you have, again, the interpolation type. So, you know, as I said, there's different options for different geometry types. And then, like, for instance, planes have a special one, quaternion, which is a different kind of rotation in the tweening. All this stuff you can see in the example files. But just wanted to show that the consistency there, and, you know, just to get familiar with really what tween two, tween consecutive, and tween through means. Another thing that's you have here is, when you're using these kind of graphs, and we can actually get a graph like here, let's say. Graph mapper. So as I change this, you'll see, you know, I'm clearly changing the spacing there. But if you want to get into it, Pufferfish also have a curve graph mapper, which you can see in the example files how to use it, but it will let you make your own graph in Rhino using NURBS curves. You can get some really cool stuff with that, so check that out. So now that you know between two, consecutive, and through, we'll just look quickly at twisted boxes. And I want to look at the twisted boxes before we get into Pufferfish. We'll look at the twisted boxes that exist within within Grasshopper and natively, and how to use them. Right? They're division count based if you use domain. So the first thing we'll have is a mesh, which is just going to be something that we populate on our twisted boxes. This is the twisted box parameter, and then this is a twisted. This lets you create twisted boxes. So that's another native Grasshopper component where you would plug each point into A, B, C, D, E, F, G, H, and get a twisted box. I, for the life of me, can never remember the order to plug those things in. It's usually trial and error for me, so I usually avoid that component. But you have these two here, surface box and blend box. Those are like the two other twisted box components native to Grasshopper, right? So we have a surface here, and what I did with that surface is plug that into the surface box, and you have this divide domain, and you're basically plugging the surface in to get the surface's domain, and then you're dividing its UV domain, in this case, with these here. So as I divide these, okay, again, but it's division count based, and we want parameter based, which we'll see in the later on videos. And then you have a height. And basically what you're doing is you're taking a bounding box. So that's your bounding box, and I'll just, for right now, I'll plug this in here to preview. Sorry, that was the wrong thing to plug in. The bounding box would be the reference box, okay? So when you morph, you have a geometry to morph. That's going to be our little mesh donut there. you have a reference box, which is the bounding box, and then you have a target box, which is going to be your surface boxes, your twisted boxes on your surface. And now you've morphed those, the donut onto the surface into those boxes, and it's all based on its relationship. That's how twisted boxes work. The relationship between the reference box, which is in this case the bounding box, to the twisted boxes is the relationship of the morphing. So right now it's exactly bounding, so these are going to fit exactly in each twisted box. So Pufferfish, I have my own morphed twisted box, which is multi-threaded. You can see it's not even calculating here, whereas this is 10 milliseconds. And the more complex geometry you make, and the more divisions you make, the actually bigger the difference in the slowness of the native one versus the pufferfish one will be, because the pufferfish one is a multi-threaded component. So the morphing is always in relationship, as I said. So what we can do actually is you can take that bounding box, get the volume, just so we have a center point there, and we can scale it. Like, so let's say that we scaled that box bigger, and we can also move it. In this case, I'm not moving it anything yet because it's in the Z direction, and we can actually use that as the reference box, right? So you'll notice that all these donuts shrank, and that's because now the relationship of this box to the donut is that the donut is smaller in the space. So here it's going to be smaller in the twisted box. So as I change this scale, that relationship is the same. Now if I go smaller here, then these are going to go outside of their twisted box because our donut is going outside of the reference box. And the same with move. If I move this, right? So if I move that reference box up, the donuts are going to go down, right? Because they have the same relationship as mentioned. So the bounding box here is above the donut, so now the twisted boxes are going to be above the morphed donuts. Okay? So it's all relationship based on that container, that bounding box to the geometry and how it morphs into that space. Now, the other one that you see down here is the blend box. And all the blend box does is you have two surfaces, right? Again, this is native Grasshopper component. Is instead of a height option like the surface box, you need to input two surfaces and you'll create the twisted boxes between those two surfaces. So you'll need another domain, two domains, and you'll want to divide them the same because you want equal amount of divisions. And you'll get something like that, right? So you create twisted boxes between. So if I change those divisions, you'll see them riding along in between those. And if I do the morph there, I'll just unpreview these surfaces, right? So now they're fitting in between there. But the relationship of how they fit in this box is still related to this, right? So if I go down, up with this, it's going to be the same relationship. Or if I scale these, if I scale the reference box, you'll again have that same situation. And yeah, like I said, like the division count, you just want to pay attention to, because if you used a different division count, like let's say we used a different division count in this V here, you're going to get weird stuff like that, right? Because now you have more boxes up there than there, and it's just going to make like a weird mess. So you want to just do like that. Okay. And And so then the difference, we'll just look at the difference, like for instance, surface box. If I get my twisted box surface, right? So it's the kind of pufferfish equivalent of this component, which has T, which is thickness instead of height, and then it has UVW parameters R and P, right? So I'll just grab this here. If I use this surface here, so we'll use that same surface, and we'll use the same height. What you'll immediately notice is there's two layers here. So that's another thing that the pufferfish twisted boxes can do that the native ones can't, is that you can have thickness layers in the Z direction, or in this case W, right? The surface Z normal is often called W, usually UVW instead of XYZ. But instead we have parameters now, right? So a parameter, we just use like a range. We'll just get a number, so that's how many numbers in the range. And we can just make one for U, make one for V, and make one for W. Okay. Right, so on the surface, it looks like it's doing the same thing as the other one, as the native one, but the difference here is because we're using parameters, we can get graph mappers. For any of these inputs, and you can change those spacings. Okay. And I'll get one for this one here. Okay. So you can change all those spacings with graphs and variable parameters. The nice thing with the Pufferfish twisted boxes also too is they're pretty optimized in the code, so they're really fast generated. Rather than if you wanted to stack, for instance, with service box, you'd have to create a lot of points over each other and then construct the twisted boxes either by various surface boxes and different surfaces, or by using this this component here by making a bunch of points and plugging them in correctly. So they're just like fast. They're just pretty fast. And then we can use those as our target. So now we can, do like, distortions like that. You can even, if you bring these down, you can go, in from the surface. You don't even have to go on the full surface. And we can stack in the Z direction if we wanted to. And we have also this component, which would be TwistedBox 2 surfaces, which is going to be the equivalent of the blend. It's going to be the pufferfish equivalent of the blend box, right? So if I plug that surface now into here, plug that surface into here, this surface into here, and I'll just copy all this stuff down and use that for UVW, and we use these for the target box. Right, so there's basically, we created the blend box version, but we're able to stack and make the divisions variable in spacing. And these also have like R and P, the refit and point sample options for the way that these things are evaluated along the surface. So as I go like that, they're kind of like falling down there. And then you can just, whatever, bake that out. Yeah, and there's our stuff that we just morphed in there. Okay, so that's kind of like just quick intro to what exists in Grasshopper Ready. There's only 4 native TwistedBox components, which is the parameter, surface box, blend box, and this TwistedBox here where you would plug each of the corner points in. And then just to show equivalent, a TwistedBox surface and TwistedBox 2 surfaces from Pufferfish. And that also exists for meshes too. You have TwistedBox 2 meshes, TwistedBox mesh, TwistedBox 2 meshes, and then you also have the consecutive and through versions of those that we'll look at in later on, which follow the same principles as these curves. So in this next session, what we're going to do is we're going to look at creating our substrate, which will be our twisted boxes that our modules will morph into. And we're going to focus on kind of ring-shaped geometry. And basically what we're going to do is use some of the TwistedBox components in a manually and parametrically derived workflow. So we'll be working in Rhino and Grasshopper. And then later on, we'll do a simple, fully parametric kind of rig of this. But I like to work between both. So what I'm going to do now is I'm just going to make a circle. I'm going to rotate it up on its side. And I'm just going to rebuild it to degree 3. So that it's no longer an arc degree 2, so that we can manipulate it easier. So what we're going to do now is we're going to get our twisted box curve. And with that twisted box curve, and we'll have other things we'll look at here. We'll start with the curve. So you'll just get your curve component, and you'll set one curve. And you'll see that it's creating already the modules around the curve there, right? They're small because of their default values. The first values I have are x and y. Now x and y are domains. So if you look here, domain size, and that's so that you can not only go through the center, but you can choose kind of which side to go off from. Okay. So if I just did one value, see it's going only inward. And this is also going to be determining on like the direction you drew your curve, which it goes by default, inward or outward, left or right. So now the curve is there, and you see how we've attached to that. What you could do if you want to stay centered is you construct a domain. And when you construct that domain, you can do then negative of this value. And that will get you centered. So you're doing positive and negative domain size. And this is a common thing in some other Grasshopper components as well. So if I just get his here and do this for y, so now we're centered exactly on that curve as we're around it. And you could also, if you wanted to be like off center, you can use a different value for the negative, and you'll see like now we're more to one side than the other, and same here. So now we're more to one side than the other. Okay. You can also use in Pufferfish, in domain, there is the two-way domain, which is a two-way domain squared, and there's two-way domain, that's what we need. You could actually just plug your value in there, and it will automatically give you a positive negative domain if you want it to stay centered. Right? So you can do that for both also. It all depends on like what you're going for in your design. So now that you have that, what you have now is also the t values. So t values are going to be the distribution of these things, of the twisted boxes around the curve. Similar to factors in the tweening that we saw. So we'll just get a range. We'll give it a number. And you'll see that we can now change that. And just like the factors and parameters in the way Pufferfish works is you can use things like graph mappers. Right? So if you wanted to change that distribution, you could also do that. Now weighted won't, I believe it won't do anything in this case because the curve is pretty much uniform. But if it wasn't uniform, if you had something like that was kind of straight and then like really curved around, something like that, if I set that curve, what you'll see is how it redistributes. Weighted basically it evaluates it based on the curve's curvature and domain rather than length. So versus normalized length versus basically t or parameter, right? So you can see that adjustment there. One's evaluating by length, the other's evaluating by domain. Usually we just use the length. So let me switch back to my curve here. And then you have rotations. In this case, you have a rotation 1 and rotation 2. It's in degrees, so if I just get 360, let's say. So the first one here is going to rotate around the twisted box centers. If yours are centered on the curve like they are now, it's going to look the same for both of these inputs, right? Because the first one goes around the twisted box centers, and then the second one goes around the curve. So, but if we offset it, so if I use these domains here that have a different negative value, so that our thing is offset a bit, something like that, and I'll offset it even further, let's say, just to make it much more different than the curve there, okay? So now it's fully off the curve, as you see there. So this value here is going to basically rotate it almost in place. So it's rotating around its own twisted box centers, whereas this one's going to rotate it around the curve. You see how it's going through and around the curve like that? So it's almost doing like tricks through a loop right now. And then this one is going to rotate it, on its own center. So that's one substrate type. Again, all these output twisted boxes, and then you could use these twisted boxes to morph any of your modules into. So the next one is, for that one, is that there's a variable version of that. And I'll just copy this over. So there's a variable version of that, and the default values, you can see already what's happening, how it's getting smaller to bigger, right? And it's twisting also. Twisting twisted boxes. So, these, it has basically what it has different is this one can take a list of domains, and it can take a list of x, y domains, list of parameters, and also a list of rotations for both types of rotation. The default input for rotation 2 is just one number, 0. If you use one number, it'll just go to all of them. That's how lists work in Grasshopper. And, basically, we can use this, for instance, this two-way domain idea here, and we can create a range of numbers. And let's say we want to create a range of numbers by, I don't know, maybe evaluating well, we could evaluate the curve. Or actually, here's a better, more interesting, is we just do a range. And for the sizes, we'll change the domain. So construct domain. So this will control like the maximum and minimum of our sizes. So 20.0. So in this case, we're just going 0 to 20. And that's going to give us a bunch of 0 to 20 range. Now the number of them should be the same number of t values. So when we make our t values, oops, there we go. We make our t values here. It's getting mad at us because it's saying you can't supply more x, y. It's because I have more x, y, and sizes and more rotations than t currently. But you see, as soon as I get more, that's just because of the defaults. But we're going to link all that together. So basically, we want to link this number to also be the amount of x and y's, right? So that will be our x there. So now we've created all these negative to positive domains. And again, you would, if you wanted to do like something like this, you would just do a construct domain here and use a different range for the bottom one. So you would need two of these. something like that. And then you'll have this kind of off range like that. So either one works. Just depends if you want to stay centered or not. Okay, so we'll use that for X. And it's telling us because the X domain start and end cannot be the same number. That's because 0 and 0 would make nothing. It's like a blank domain. So this needs to be bigger, at least a bit different than 0. So that you don't have a domain that is 0 to 0, which is invalid. It's nothing, basically. And we'll just copy this down, and we'll make, we'll make this for y also. These values are a bit high, so let's just bring them down. And you'll see at some point it stops rotating. That's because we have more x, y, and t's than we do of rotations. So what we need to do is, give it, if we want a rotation for each one of those, we need to give it a rotation for all of them. So we'll make another range here. The same amount of numbers, but we'll give it a domain. And again, these have two different domains, right? It has the domain here. You're creating a range for the positive of the domain we're constructing and the negative of the domain we're constructing. Okay. And so what we'll do here now is we'll take this, and this should be, want rotation, so it should be something like 360, right? So I'll just make something here that's a kind of higher value for a rotational value. Okay, so we'll get that here, right? So now we have the same amount of rotations there, right? So now each one has its own rotation. Okay, and then you can do the same setup for the second rotation here, which is going to be the rotation around the curve. So you'll see that it's moving, it's kind of like twisting and coiling around the curve, like a snake, whereas this one is twisting on itself. Oh, sorry, this one is twisting around itself and then twisting around the curve. Okay. And what you can what you could also do is you could do a mirror cut numbers, and we can mirror the mirror index is 0. What we can do is we can mirror cut it at the in half. So if we divide division, if we divide this by 2, mirror cut numbers is also part of Pufferfish. So if you divide that by 2, and we'll want a sorry, I need list length. So yeah, so now we have 20.5. We should have an even number, so we'll just make this is steps, so that's why you have that one extra. So we make that 41 so that we get an even number here, which is 21. Mirror cut that, and now if we look at the list here, it's going to be starting at negative 1.0444 and ending at the same one, and it's going to be 44 values. And here we actually want to do list length in Pufferfish. We have number, and we have the I've moved some of these around recently, so it should be last index. There you go. That is in number in Pufferfish in list last index. Actually, it doesn't seem to matter there. Subtract that, subtract the division by 1. So yeah, so it's just the list length divided by 2 minus 1, and also Pufferfish has a kind of useful little x minus 1. It's simple, but used often, so that's why it's there if you want x minus 1. And so you have your 42 values, same that was here, 42. And basically what we're doing here is we're creating like a symmetrical list of numbers, right? So it ends and starts at the same numbers. And so if I plug that in, I'm just going to copy this all down for now. Turn that off, just so that we have this one without this next step. So if we plug this in here into x, okay, and we do the same kind of thing for y, and we do the same kind of thing for rotation, for both the rotations. So what you've done here now is you've made a system that always will, if you see here, it connects back to each other. So basically, in this case, you've just made a symmetrical system. And when you do symmetry, you need even numbers. That's why this is like glitching out. And even numbers, when you're using a range, would be an odd number. So we're going to restrict this to odd numbers. Okay, so by having an odd number, by doing a range, you actually get an even number of things because it's odd steps. It's always plus 1, so you have 30. So you've just created like a symmetrical system here. Okay, and yeah, so the next thing we'll look at now, I'm just going to start to close those off. So next, what I'm going to look at in Pufferfish in TwistedBoxes is I'm going to look at there's also a TwistedBox tube. Sorry, TwistedBox. Yeah, TwistedBox tube. Sorry, sometimes I rename stuff and I just forget what they're called after doing all these components. So TwistedBox tube is going to be able to do all the same stuff as this. So take into account what you've learned here, and I'll just copy another one here. Well, the TwistedBox curve uses a radius, a thickness, U, V, and W parameters, a weight, and then there's an offset. So you can actually offset this one from the curve with a domain. So similar to how this uses size domains for x, y, this one uses a radius and an offset. Okay, so if we just get 10.0, whatever, get our radius here, and we'll get a range. Wrong one. The thickness here is, so you have an offset and then a thickness, and that's kind of, the thickness is the inward dimension there, so you can see how those are, getting bigger inward there. And just so you can see what this is doing, if I just did this on like a line, right, you'll see, if I just bake this, actually, is it going to be a lot? 360, maybe not, should be okay. I just want to show you like the type of geometry that it's making. Okay, show shaded. So that's the kind of, these are just the BREP forms of those twisted boxes, but that's the kind of geometry it's making around the curve. So we'll set this curve back in here. So that will be your thickness. UVW is going to be, first is going to be divisions around, so there's going to be divisions around the curve. So divisions around the curve, and then, divisions along the curve. V will be divisions around the curve. And then W will be divisions in the thickness of the curve. Okay, so if you make it thicker there, you can see, if I look at that profile there, that kind of like spider web, because I'm adding more in the thickness. And it has also the same weighted option that I showed you before on the curve. If you had like something with more curvature, it would be weighted based on the curvature. And then there's the two rotations. I will just grab it from here, the rotation range. And you want, the rotation is going to be around the radius centers. So rotation twisted box around the radius centers. And actually this one isn't the variable one. So here we would just use single numbers for those. So just use these. Okay, so now you can rotate around that, and again, they look the same. Let me just shrink this a bit, just for simplicity right now. Okay, so you have something like that, and you can then offset it with a domain, an offset domain. So if we grabbed, like, I don't know, one of these that we're using before, let's say something like this set up here, where we varied the domain here. It's just one number for this one because this isn't the variable one. So if I bring it, you know, like that, it's going to be further off from the curve there. And basically, again, you have this one, which, as you see, it rotates around itself through its centers. And then this one's going to rotate it around the curve, right? Just like the other one there. What's cool about the TwistedBox pipe, TwistedBox tube, is that you can use graphs on it, and you can even like open it up. So you use the graph mapper here on the V. And if I go to graph types, and go to sorry, I wanted to go to V, and to the V, you see how you can start to change those spacings. But if you go, you see how in this area here, it's making a connection, but you could actually instead just make the graph not 0 to 1, or even just make the range not 0 to 1, and you can open that up, which is really cool. And you can do that in both directions. You could do that in the U also, right? So if you wanted to only be on like part of the, if you wanted to not do the full connection there. And the orientation, it's just the way Rhino makes these things. It can flip sometimes like that. So if I just lower the amount of these real quick, have like less, like that. So if I bake this, you see how it's like an open channel there? That's because of this is not 0 to 1. Now the TwistedBox tube also has a parameter version, which you can find examples in the example files, and you can it would follow the same principles as what we did here. Is and again, you don't have to do this setup. This is like super customized, and maybe too much than what you need, but it just shows you the level of customization you can get into by accessing parameter values instead of division counts. And that's kind of like the takeaway here. So another thing that I like to do now is you can go through and you can start to edit these curves, and you can see how those will start to follow along with that. So that was what I was talking about, like this kind of manual and not manual workflow. And in fact, just for quickness, if I morph if I just did like a simple mesh box, and we'll give it one face each, just so it's like just a really simple box. And did a bounding box on that. And then I'm connecting the mesh box to geometry to morph, reference, and then targets will be these boxes, twisted boxes here. And this is just so I can visualize, and I'll just bake this real quick, just so you can visualize the flow that's happening there and how we've opened up that ring shape there. Okay, so if I go to Arctic, right? So again, it's a little boxy again because I'm just using a mesh to display it, but you get the idea of what like opening those things up and doing that does. So I'll just save this real quick. So now that that's like that, so basically we'll look at now, there's also twisted box 2 curves, twisted box through curves, to have consecutive curves. We'll look at the twisted box 2 curves, and I want to compare it to another component. So twisted box 2 curves requires 2 curves as an input. So 1, 2. So you have these 2 curves there, and we'll set them both in. So set 1 curve, and then set 1 curve, A, B, okay, and then the 0, you know, it's just has like a very few for the defaults, and thickness will be the overall thickness outward. So or in this case inwards, but if you flip your curves, I'll just flip them both, it will go outwards, right? So it's just based on the curve direction. And then we'll give it our ranges. We'll make a separate one for U, V, and W. And that's kind of like a lot. Probably don't want that many. Or maybe you do. But in this case, I don't want that much. I just want one level of thickness. These should be, they can be integers. Just makes it easier to work with. All right, so we'll just do one in that direction, and you can do even one in this direction, right? Or you could do multiple, like if you wanted more rows in that direction. And then this will control this direction. And again, this is all editable with graph mappers as well. If you want to control different spacing, you would just plug a graph mapper between. And these have refit and point sample options that we saw before in the curves, and that has to do with these curves here. And it has weighted options. But what's interesting about this is when you start using multiple curves, is you can start to play with then the proportions and shapes of these curves. So for instance, maybe you want the top to like kind of flare out a bit like that. Maybe you want the bottom to come in a bit more, right? So you just start to kind of sculpt them based on just this curve wireframe, essentially. And you can already see a kind of ring shape happening. If you did something like that. So with the TwistedBox 2 curves, you also have the consecutive and through. We'll look at like TwistedBox through curves here. And it's going to have the same inputs. And again, remember our curves that we did in the beginning. You have normalized, equalized, weighted, interpolation type. So we won't go over that in depth, but you have the UVW, thickness, and C. What that lets you do is maybe you want more curves. Like maybe you want 3 curves in this system. So I'll just go here. So now I have this 3 curve system. I'll copy all this stuff down here. And we only need one of these now. And remember, we right click here first, set multiple curves, and we set the 3 here. And then we plug in our values similar to the TwistedBox 2 curves above. T, U, V, W. And we have to flip this one because we flipped the other ones before. All right, so now we have a three curve system. And you can, start introducing like what does that third curve do, right? And this has equalized, it'll be equal now because I think pretty much because of the shapes are pretty proportionate. But you can make this even disproportionate too. On one side, maybe it's more like that. You can add, again, more divisions as you want it. Like maybe you want to morph into the thing like that kind of shape there. And if I just morph into that, you'll see the kind of shape, just to visualize the shape that we're working with, and then we can morph cells into it. Right? So that's the kind of shape that we're working with. And if you get a more interesting thing to morph into there, and we work with connections, which we'll look at, you'll start to get really interesting geometry. Okay, so in this part of the tutorial, we'll look at a few more TwistedBox options on ring shapes, and then we'll move into creating our own kind of ring rig. So we're going to look at a few more from Pufferfish. So what I'm going to do is I'm going to make a circle here. I'm going to rotate it up like this, and then I am going to copy it over. Then I'm going to select this one and I'm going to scale it. Sorry, copy it and scale it. You can do that with Shift and Alt to copy and use a modifier. Okay, so we'll end up with something like that. So you have these four rail curves. So what we'll do now is we'll bring those curves into Grasshopper. And it's important the order. So you want to select them like in an order like around what would be this ring shape. So set multiple curves from the component, and I'm just going to select them around. All right. So the component we're going to get is from Pufferfish, which is called the TwistedBox sweep, which takes 4 rail curves, and actually, you could set each one separately as the way that they go in there. But in this case, I like to have things in one parameter here. And then what you can just do is you can do like, because it will always be 4 in this case. So you can just do explode tree. And actually, if you just graph this, right, you'll have your 4 there. Right, I just think it's like just a more organized way. Right? So now you'll have made your TwistedBox sweep. And I'll just rebuild these so that they're not arc circles, just so we can deform them easier. So I just rebuilt them to 8 control points. So what's cool is that you can then just turn the control points on and start to edit this rig here, and really start to fine tune, what your kind of overall ring shape will be. So yeah, I mean, just play with it whatever you want. And then there's the T values, which is the the divisions around the whole network there. So you would get like something like range, as we've been doing. Again, like just the consistency between all the components of Pufferfish is they use these parameter values for either parameters or factors instead of divisions. Yeah, and then so if you wanted 100 of them or less, and as always, you can use stuff like graph mappers. So if you wanted to kind of play with the spacing there. And you could also, there's a weighted option, and that just weights the spacing either right now it's like by normalized 0 to 1, like, but equalized division. But you can do it by curvature, which is what the weighted option would be. You could see it changes a bit, right? So now it's dividing from 0 to 1, but based on the domain instead of the equalized divisions. Okay, so you see a small adjustment there, and the more curved you made these things, the more different they would be. So along with this component, there's also a variable option. There's the TwistedBox sweep variable, right? Just like how we had the TwistedBox tube variable before and the TwistedBox curve variable. Yeah, you have the sweep options as well. So the inputs here look the same, but the difference is that you'll have a T, which is divisions for each parameter, which can give you like more custom control over that setup. So I'll just copy these over. And with those copied over, I'll just grab this here, and this. Okay, and we'll set those curves. Just remember, do it from the parameter, not from Rhino first. So set multiple curves. We'll just select them around in the order, and we'll plug those all in. Okay, so first it looks the same as what we did there, but again the difference is these t values, and you want to make sure that you have the same amount. It will still work if you don't, but it could look weird. Like if I give this one a different amount, you see like some of your twisted boxes are going to all like the remainder ones, because of longest list Grasshopper rules, are going to go to like the last twisted box point there. So it's not really desired. Maybe you can find like a cool use for it, but in this case, it's not really beneficial. What you would do is have one range made, and you would get maybe different graph mappers, and you can use a different graph mapper for each one of those t values. Right, so right now it'll all look the same. It'll all look the same here, but what I can do is then edit this graph, right? And you can start to maybe you want this one to kind of be a little bit sharper there. But the important thing is they're the same amount of parameters, so you'll get the same amount of points to construct the same amount of twisted boxes. And again, this one also has a weighted option, which will weight all of the parameters or not weight them. And again, you can go through and you can have some fun with these. Let's say you want this to be like really dramatic. That, right? Okay. So then, what we can look at is also, I internalize it. You can also take these and you can do stuff like surface-based stuff too. So, for instance, maybe you have a surface that you've made or pulled from somewhere that you wanted to create this kind of twisted box stuff on. You could, I'm just going to loft these that we already have. So, and I mean, in essence, it would kind of be the same as this, but offset outwards. But let's just say that you had a pre-existing surface. And we'll go to shaded so we can see that surface. Okay. So there's our surface there. So what we'll get now is our twisted box surface. And we'll just put our surface in there. Don't know what happened there. That was weird. Not seen that before. Because, okay, now I know. Because this is a super dense surface. So it doesn't need to be. So let's just remake that. So we'll rebuild these curves. Actually, how many control points are? Yeah. So I think I just have like a weird loft option. So because I have tight on, let's just do normal. And don't, that's why, see, I rebuilt it accidentally with 1,000 control points. So it just made this super unnecessarily dense surface. So we're just going to say do not simplify. Yeah. So now if we set the surface in, yeah, see, it's all good. And now, you know, by default, it's going to go either inward or outward. And that's going to depend on the direction of your surface. So you could run the dir command, and you can swap the UVs. So if I swap the UVs, you'll see it will be going out now. There's not many divisions by default, so that's why it looks kind of weird. But we'll get these ranges here. And I'll just copy, you know, because we have a thickness U, V, and W. So it would be like U around, V across, and then W would be the thickness. So we'll get the thickness here. 30, I don't know. Just making this up. We're not really working with real dimensions here right now. Yeah. So that would be your thickness, and then you would have your U parameters. So now it's much different there. And you'll see it because of how far we're coming out. You'll see how it gets a little weird, right? Because the boxes are going to self-intersect. Another thing to note is you'll see, because of the way your seam is, will heavily influence the directionality across the ring. So you'll see how it's kind of going diagonally across. So we can change that seam if we reloft, but let's just bring this down for now, like something like that for now. But yeah, that seam is really going to mess with us down there. So it's something we want to look at. Our V, right? So that's how many we go in, you know, that direction. And then our W would be how many we do in the thickness. So if I made this thicker, right? So that's how many we'll do in the thickness of that. But usually we'll just do like one in the thickness. We'll bring this overall thickness down, and we might have like less of these, maybe some kind of setup like that. And what I want to show you is like you can change the seam. So surface seam. I always forget the name. Yeah, surf seam. And then, so you can move this seam if you want, right? But that's still gonna like keep the direction of the seam. What you really want to do is remake that surface and change it at this point here, right? So we want to bring these so it's more even. Just by eye, should be good enough. Okay, so now you have something like that, and we just set this one in. So we set that one in. And again, there's like that flipping thing again. But what we can do, instead of running dir in Rhino, in Pufferfish, you have a swap surface directions component. You can just do it directly in Grasshopper if you feel like it. By default, it's UV swap. I don't know what happened there. That's weird. Surface. Oh, okay. So that's like something weird that doesn't happen in. There's just like some weird stuff. can always find these weird bugs in Rhino 6 so far that used to work in Rhino 5, but for some reason, yeah, doesn't seem to work in the newest Rhino 6. So we'll ignore that for now. But if you are in Rhino 5, until I investigate that, you could just UV swap it like that. Anyway, so we'll just do it here. Direction swap there, and yeah, so that's something I'll make note of and look at in the next update. But you see now how it's less, like it's all less intersecting at the bottom here, like less self intersection, so you'll get like a nicer shape when you morph in onto that. So yeah, and then you just, as with everything else, you just play with these values until you get the thing that you want. What you can also do is you can do, if you had two surfaces, so I'll just scale this in, right? Maybe we want it like thinner down here, so I'll just like move that down there. Again, you could be more precise with this as you like edit your surface, as you're doing your design. But you'll have the TwistedBox. The TwistedBox, you can do through surface will work. We won't go through all of them, but there's examples in the example file. But for instance, in this case, TwistedBox two surfaces. Because if you do, and again, this is why I showed you the curves in the beginning, because of the consistency between all the components of Pufferfish. You can use the through surfaces, and you'll know kind of the inputs based on those through curves. The same with the consecutive surfaces, and you'll know what they do. Consecutive is between each one, through is through the entire set, and then two is between two. Okay. So we can get the surfaces. Set one, and then set the other. Right. So now you're making it between those surfaces. So if you get there's no more thickness, right? Because your thickness is now going to be, whatever that you define those two surfaces as. So I'll just get U, V, W, and yeah, and there you go. So now you have your thing like between those two things, and you can move this around. Like say you wanted it thicker at the bottom for some reason. Yeah, or you can just change the scale of that. And again, with all this, you can use graphs and whatnot. And the other cool thing is that you can kind of like open up the ring if you wanted. So like if I went back to this one here, just make a copy of it. Now I'll make a copy of this over here. Set one surface. And I'll move the seam to the bottom, because let's say we want to open up the bottom. So surf seam. And I'll just move the seam down here, something like that. So what you can do now is in your U divisions, you can get a graph. And you can play with the extremes there, so you can see how it opens up there. right? So you can create a kind of ring design that has an opening. You can do that also without a graph by just defining the domain here. So if I just put this here and just define this domain, to just be different, a little bit inward from 0 to 1. So like if I went to 0.25 to, you see, right? Okay. And again, that's just the beauty of using the parameter values. And you can do that in all directions as well. If you want to do it in this way, like maybe you didn't want to be fully on the surface. Maybe you want it to be a little bit, you know, inset or to one side. So yeah, just the possibilities of using parameters. And then we won't have time to go over it right now, but there is an accompanying component for each one of those for meshes as well. So if you had a mesh instead of a surface input, it would be basically the same idea. So if I go here, you know, for instance, TwistedBox mesh, right? It's going to look a little different, right? There's just W, there's no UV because mesh is going to be based on the mesh faces. Like you don't divide a mesh by parameter the same way you do a surface. It would just be, you know, whatever the mesh face is, that's what's going to be the face there. I can actually quickly just take this over here. If I just make this a mesh, let's see if this will work. If I do like a simple mesh, yeah. So if I got something like that, like so, say I use that mesh there, it's basically just going to be and we'll flip the normals, right? So I just flip the normal so it's out, right? So so each one of those faces is going to become a TwistedBox, and it by default has 2 layers of thickness, which is the W here. So we can make it 1 if we want. So we can have 1 layer of thickness there. And yeah, and then we'll give it a thickness. Yeah, so, and then again, that has the same component for like, you can do between for that as well. You can also, like if you had Weaverbird, you can do like a Catmull Clark, let's say. So you can do like a subdivision of that. Let me just hide this. So you can like do a subdivided, right? So now I've subdivided the mesh. Oh yeah, that should be L levels, right? So by subdividing the mesh, you can create more twisted boxes on that surface. Okay. And this is all stuff that you would just then morph into. Okay, so the next thing I want to do is to kind of build up a more custom rig that doesn't rely so much on the pufferfish stuff, just so we can see how to use the twisted boxes and kind of build up a system natively. So just save. Okay, so what I'm going to do is I'm going to start with a new new file. Do I have a file? No. We'll just start. We'll just use a native. We'll just build a circle actually in Grasshopper. Let's do that. So we'll have a circle. Okay, and we'll have a XZ plane, and that's going to be our plane for our circle. So let's just zoom in there. Okay, let's just move this out of the way from the other stuff here. So we'll just set a point somewhere, I don't know, over here, just so we can work over there. Okay, so there's our circle. And we'll, just give it a size. So, again, this size would be, whatever your ring size would be. It would be like the inner size of the ring. And what we'll do is we'll just we'll adjust the seam of the circle. And this is just so that we can kind of rotate it later on. So we'll get the seam. Seam reparameterize, which will make the curve's domain be 0 to 1. And then we'll just get a arrow here. So you won't see, but basically it's just deciding where the seam of that curve is. If I did like endpoints, right? So it's just deciding where that seam is. The next thing that we're going to do is we're going to construct, basically we're going to construct twisted boxes along this curve, but in a way that we keep the inner dimension of this circle unobstructed so that it could fit on a finger. So we'll just get curve. I'm just going to use this parameter just to organize things out over here. And the first thing we're going to do is we're going to get some unequal division points on the curve. So we'll get a evaluate. And we will reparameterize it and get a graph. Actually, I want to bring this down here because we're going to be using this input into a lot of other places. And we'll just get a Bezier curve, and we will, we'll just create a range basically, as we've been doing. And we can do some kind of spacing like this if we wanted. And so the reason we rotate is so that we can change also the location of that spacing, you see. So the next thing we're going to do is the part that is going to let us kind of keep this system unobstructing, which is we will do a kind of curve, a line intersection, yeah, to basically create that. So we'll do shift path, shift list, sorry, and we want to make sure that wrapping is true, which it should be by default to true. And we want to shift the list by 1. We want to shift points and the parameters. Sorry, points and tangents by 1. And what we're going to get now is we're going to create a vector. So we'll use well, a line basically. So the line start SDL, start direction length, and the start will go here, and then direction will be there. And length you can just keep as default because we're going to use a mathematical intersection in this case. Sorry, and then this one we'll just do the unshifted, right? And then we'll just do the line-line intersection, line-line. Line here, and we'll just take these lines and intersect them with these lines, and that will give you points of where those tangents would intersect each other. And then what we're going to do now is we're going to create like an attractor point. What's this saying here? Lines are antiparallel and cannot be intersected. Well, it worked, so I don't know. I don't know why it would say that, because it's clearly working. Yeah, 21 points, 20 input, 15, 15. Yeah, I don't know. I don't know why I would say that, but seems okay. So anyway, so we'll create a point at the bottom of the circle to use as an attractor point. So what we'll do, well, actually, it doesn't even need to be at the attractor point. We can do like a point on curve, which is this kind of little thing here. Okay, and that will just let us get a point around the curve. You can see it traveling around there. Okay, and what we're going to do is we're going to measure from the points A. I see now there's like a null. There's like a null point down there. I wonder if it's. I bet it's the. Let's just see if that helps. No, doesn't change anything. Sorry, just repositioning this here. You know, maybe if I. Let me just try something here. Ah, that was the problem. So the problem was using range. It was giving me like its steps, so it was giving me as like an extra number that I didn't want. So let's just stick with series from now. Well, at least you get to see some troubleshooting. Okay. So we have these points now, and we're going to measure the we're going to measure the like from these points to this point that we have traveling around, so that we use it like an attractor. So we'll get the closest. We'll get actually we can just do pull point. I like pull point. It's just very diverse component. We'll get P points A, and that's just so that we get the distances. And then what we'll do is we'll just reparameterize those distances. You can use it with you can use the remap numbers, or you can use Pufferfish's reparameterize numbers, which will just automatically make it go 0 to 1. Or if you want, you could invert it 1 to 0. But for now, we'll just do 0 to 1. So what we'll do now is we'll offset these divisions in the y direction. So I'll get another graph mapper. And we can do something like a conic. And then we'll get the bounds. And we will then remap to a new domain. So we'll remap the graph to a new domain. We'll get we'll construct domain, and I realized I don't have the bifocals, but I'll give you guys these files anyway. Sorry for that. And we'll just construct this. And we want to move in the y direction those PA points. So we're going to move these points in the y direction, right? So we're kind of, see how we're like offsetting them from that circle? And it's based on this point here. Okay. Then what we're going to do is we're going to mirror those points on the other side. So what we'll do is we'll just get the XZ plane, and we'll put an XZ plane at this point here. And we'll mirror. Right, so now we have it on both sides. And we will, just to keep the video at the correct time limit, I will stop this video and we'll continue on this rig in the next part. Okay, so we'll pick up where we left off. And actually what I want to do is this part that we were making here for our ring rig, I just want to copy this into a new file. So just want to get some stuff out of the way there. Okay. So the next thing we're going to do is we're going to make some adjustments to the scale of these this kind of point grid that we're making around this circle. So we will get graph mappers, and we're going to basically use this same distance to our point that goes around like this. We'll just get our our data from that distance. So we'll just plug that data from the reparameterized range, because it's already 0 to 1, into our graph mapper here. And we'll just use, I don't know, in this case we can use conic curves, seem to make some nice scales. And then we will just remap those values. And we're going to construct a new domain. And we don't need to put a bounds in here because it's already 0 to 1, and what we're inputting in is 0 to 1. So I'm just going to move this up here because we'll need 2 of them. So I just want to make some space for them both up there. Okay, and then we'll get some, I'm just, I don't know if these are correct values, but we'll just get some sliders here to determine our range. And we'll see, as soon as we plug this thing in and get it all set up, like if it's too big or not. And we'll scale. We'll scale the moved points here that went into the mirror. We'll scale those by these factors, and the center will be the it will be the center of this circle. You can just deconstruct arc. You can use area also, but this will give you a center, which would be the base plane here. Right? If you use the base plane, you can use it as a point, basically. Okay. So what we've done is now we've created a scale factor for those moved points. Okay. And then what we're going to do is we're going to do the same setup for the mirrored points. So we will just like copy we'll just copy the points. It seems to be maybe we should use area. It seems something is going on weird with that plane. So if I just use area here, yeah, that's what we're, oops. Nope, wrong. Plug the wrong thing in. We're going to get the centroid and put it there. And then we will do the same thing for the mirrored points. So we'll just, I see what I did. See, I put the construct domain, I put that into S accidentally. It should be there. That's why it was looking weird to me. There you go. Because we want to scale around that center, because the idea is we don't want to go into that circle. Okay, so don't do that mistake that I did plugging into S. Which means we could use actually the deconstruct arc. It doesn't make a difference computationally here, a big difference, but you can see here like 13 milliseconds versus no calculation. It's good to use these tricks and kind of use area as less as possible. Okay. So that's going to be one of our that'll be one of our scale, and then we'll need another one. So I'll just copy this whole thing down, and instead what we're going to scale this time is these mirrored points on the other end. Okay, so now you'll have separate control over each side there. Okay. And then what you're going to do is you're going to get line components, and you're basically going to create lines going from this two scaled systems here. Right, so now you have these lines going around. And it's important actually to make sure that you don't go under 1. So what I'm going to do is I'm just going to set the minimum to be 1, because again, we don't want to go into that circle, which, for instance, if this was a ring, that would be where your finger would go. So by just setting the minimum to 1 prevents us from scaling under. And then we'll make another set of lines, and these lines are going to go from the moved points to the mirrored points. Okay, so now you have these two sets of lines. I'll just hide some of this stuff there. So now you have these two sets of lines going around this circle. And what we'll do here now is we'll loft those lines as straight segments, and then convert that into twisted boxes from surface, and that will complete our base rig. So we'll just get it in twine. All right, so in twine we'll keep things in their own list, but so that you can create a tree. So if we visualize this, right, so that's going to be your lines from here, and then 0, 1 will be your lines from here. Okay, and then we'll loft. Right, so now you've created this loft around. And what we'll do now is we will get the loft options. And we're going to turn this into straight segments, which is 3 straight, right? So I tend to use panels for parameters that I know I don't want to change in the future versus sliders for things that I want to be variable. So yeah, so that's the idea there, to create this kind of faceted ring around there. And then if you want, you can close it by making closed true, so you can have like an open ring system like that, or a closed ring. And if I actually just go back to the beginning here where we first made our circle, if I adjust this seam, I can change the orientation of that. So if your ring is at the bottom, it would be 0.75 from the way that the ring is created. Circles are created in the XC plane. Okay, so we'll go with closed. So then what we're going to do is we're going to deconstruct the BREP. We're going to get the faces, and from each face we're going to create, between each set of faces, we're going to create a twisted box system. So what we need to do first is we need to get these in pairs of 2, and how we do that is we just flip the matrix. So flip matrix. So now everything is between these two things is paired up, right? So they're paired like 1, 2, 1, 2, 1, 2. And what we'll do now is we'll use the TwistedBox through surfaces. You can use TwistedBox to surfaces also, but then you would have to split up the list into A, B, which you would just use this then. But I'm going to use the TwistedBox through. Okay, so now we've made a TwistedBox system, between each one of those, and we'll make a range for each of those. So range, and range. So for this component, if you're interested in all these other inputs, please look at the example files because it's all explained in the Pufferfish example files. But we also explain them in the tween curve components of what they do, like weighted, equalized, normalized, interpolation type, refit, and point sample. Same idea as the curve ones, but in this case we don't really need to mess with any of that. So I'll get a twisted box parameter. I just like to display it in the parameter. And I will hide this. Oh, I recalculated, preview off. And I'll give it, in the Z for now, I just want to give it 1 in the Z direction. And I'm just going to bring these down just so we can see what's, what's happening there, right? So if I brought these all down to 1, basically each one of those faces is going to become a twisted box that we can morph into. And again, the important thing is that now, no matter what, we don't intersect that circle. So if I go around and I change, for instance, this divisions, and what's interesting, if you get like real low divisions, you start to get stuff like this, right? Which could be really cool ring shape, and it ensures that whatever your ring size is, the finger would fit through that opening. And then you can play with your parameters here to control your domains here to control each side, like the height of each side, and just to really define kind of the shape of your ring system. And you can also play with your graphs. You can get sometimes like some stuff like that, which kind of like bellows out there. And then these parameters here, are based on the attractor, and they're going to determine like the thickness. So at the top there, or at the bottom, and again with a graph. And you can use different types of graphs also. You can use you could probably use sine wave if you wanted the kind of sine type of spacing. You can do some kind of like weird, weird thing like that, right? But for now, I'll just stick with the conic graph like that. Okay, so that's basically gonna be our rig there, right? So that's our rig. Let's call that. And again, like so, if you wanted to put more divisions per face, also you can divide by face, or you can divide completely around the ring there. And this division over here by face can also go in this direction too, right? So you can go in I guess in this orientation, the Y direction, and you can also stack twisted boxes in the Z direction, okay? So now that we have our ring rig, we should look at some some modules that we can put into the twisted boxes. And we'll start with some pre-made modules, and those exist. Mesh Plus has a tab which has a lot of interesting cell types that you can use already pre-made. And keep in mind that we're just working with this rig now, but all the other systems for twisted boxes around like curves and surfaces and meshes that I showed you in the previous video, you can use any one of those systems and populate them in the same way. Just for the remainder, we'll just work with this custom rig that we've made. So I'm going to go to Mesh Plus here, and if you go to the Volume tab, so all these are cells that we can use pre-made, and they have parameters. And one of my favorite that just looks kind of instantly cool is the bat wing, right? So I'll look at that. Okay, so bat wing, and let's see, I'll just pick a few that we can look at now. But I suggest that you go through all of them just to see what exists there pre-made already. Let's see, what else can we look at? We can look at the box, and we can look at also, I don't know, maybe cross. So let me get cross here. Okay, so all of them, all the volume components from Mesh Plus, they start with the same thing, which is two rectangles basically. And keep in mind that the size of the cell when you create it is irrelevant, because as we've discussed in some previous videos, I think the first one is that it's the relationship of the bounding box we'll put around the cell to how it morphs in there. So I like to make them a bit big just so I don't lose them in Rhino. And I just made two rectangles here. I made one, and then I copied it up, which is important because you want to make sure your rectangles are in the same orientation and drawn the same way. Okay, so just going to go to it's also important that when you create these, they should be squares. So I just hold Shift to make a square, just so that the proportions are correct. And I'll just go to curve, and I'll just get two of these, and I'll set one curve here, and I will set one curve here, and just hide these. Okay, and just internalize these for when I give you guys the file. Okay, and put your bottom curve in G0, top one in G1, and you'll see a cell is made there already. And I'm just going to plug these in to the other ones too, because we'll just use the same curves there to make these. Okay, and I'll just unpreview these. And the important thing to look at here is when you're making a cell is the edge conditions and how those edge conditions will join together. So if I bake this and we just take a look at it, go to shaded mode, and I actually want to display color back faces. So I usually color the back faces red from display just so I can see what's the back and what's the front face, which will be important in our welding and smoothing later on. So if you look at this thing, the thing you want to look at is if I copy this thing, does it connect to the other side? So you see here that it does connect to the other side, right? So that's what we're looking for when we create cells that will propagate. And same with this, if I copy this in the other direction, it also connects, right? So we're looking for things that connect to each other, and this is important for the smoothing steps. Now, if I just take this cell, I can just take this cell directly, and I can get our morph to TwistedBox. And we're going to take this geometry and we'll get the bounding box of that geometry. Now, what I like to do is you can do bounding box, but for it to be safe, because later on we'll do some things where the geometry is kind of outside of the bounding box. What you really care about for the bounding box for things to connect is the naked conditions. So you can get naked Weaverbird's naked boundary is what I like to use. This will just give you the naked edges of that mesh, right? And I like to make the bounding box around that naked edge. And this is, you know, when we look later, when we show something with like morphing and blending different types of cells on the same system, they might have different heights and all that, but the connections should all be the same geometry. And so our bounding box wants to look at that connection geometry so that we have one size bounding box. So our reference box, and then our target is going to be our system that we made here, right? So now we've put that cell onto that system there, right? So we've propagated it there. So if I bake that, and we just take a look at it, right? So everything's connecting, okay? Now the thing to notice is the normals should never be like from red to gray. Like it should always be gray connecting to gray and red connecting to red, okay? And because that will really affect the smoothing. So what we want to do is once we morph it, we're going to want to weld it and unify normals. So you can use Pufferfish's rebuild mesh. And the things we're going to want to look at is unifying normals, combining identicals, and welding. So I guess get a boolean here, boolean toggle. So unify, right? So we'll unify and we'll combine identical. Important to join the meshes first. So we want to put those into join, flatten, right? Join all those meshes together, unify them, weld, combine identical vertices, and then just to be sure for any discrepancies, we'll just set a welding tolerance to. So anything that's within that tolerance will also weld together. Okay. So if I bake this, so that was prior to welding, and then this will be after welding and unifying. Okay. So you see how here we have a transition where it goes gray, gray, and then gray, and then, but here it goes gray to red. Whereas here now it goes gray to gray, right? So you can follow the gray all around, you can follow the red all around. Okay? And following it means following it at the connections between each cell. So now that we've unified, we can then do Weaverbird's smoothing. Sorry, I didn't mean that one. I meant Catmull Clark from Weaverbird. And we'll give it a smoothing level, so in this case 3. And just turn off those previews. So if I go and bake this out, you see how we smoothed everything nice there. Whereas if I didn't do that, you're going to get something like that, right? So you see that seam there? That seam's no good, especially if you go into like a rendered mode. See how you can see that kind of ugly seam there? Because the normals are in different directions. Whereas this one is all nice and smooth because we've unified all the normals. Okay. And the other thing to look at in a system like this is thickening. And there's kind of flaws to thickening, especially in this one. So I'll just get Weaverbird's mesh thicken. And I will change the distance for thickening. Okay. Now the hard part about thickening is that it's, especially in a geometry like this, it's very easy to get self-intersections, which are not going to be good for production of this ring. So if I bake this out, and I'll go into rendered so we can see things easy, you'll see down here there's a lot of weird stuff going on because things were too close for the thickening. And you could also thicken per vertice, but it's hard. It's especially hard to calculate because you have to calculate a lot of different vertice distances. It's not as easy as just using an attractor. I mean, you could, but chances are you'll still get this self-intersection. So what we'll look at in a later video is to take this geometry and then use a volumetric thickening through, for instance, Dendro, and I'll even show the small parts with ZBrush to make this 3D printable so we don't have to worry about the self-intersections there. But if it's just for rendering purposes, this is then acceptable. So for now, I'll just ignore the thickening part. And we can just look at the other, cells. So I'll just come here. Just want to zoom to that thing there, shaded. So if we look at, for instance, this cell here, which is called IWRP, which is this kind of like boxy latticey cell here, we can just replace using shift to control to put those cells. And we get an error here that says we cannot is this outputting more stuff? That's weird. Okay, that was because the other one had a continuous edge, so I just kind of overlooked the bounding box. You want to put the union just to get, because this doesn't have continuous naked edges. They're like kind of in each corner. So something like this, when smoothed, will give you something like that. So if I render this, let me just zoom into it. So now you have this kind of interesting bone-like structure. So you can do the thickening thing here also, and then we can, do the volumetric thickening later on. But another thing you can do with geometry like this is because it has these. It's not just a continuous edge that's naked like the bat wing. What you can do here is before smoothing, you can close. So after you weld it and all that, you can use Pufferfish's close mesh, which will close it, find the holes, close it, weld it back together automatically, and you can do that. So that will close all the holes. So now what you would get is something like that. It seems like it missed some holes in that geometry, and I think that's because they come around like the corners like that. Yeah, definitely missed some. So it's not always doesn't always work. Let's see here. So I think it's the welding actually. Let me bake this. Let's see what happened. Yeah, because there's some non-manifold stuff there, that's why. Well, either way, we'll show some other examples where we close out. Maybe you can even, I don't know if that works, like twice. Probably not. Just the way this jump. Oh wait, did that actually? Okay, it did actually work. Sometimes you have to just do it multiple times if it misses it, because the way it calculates it, it finds all the holes it can close and then closes them, which will give you a new type of mesh, and then you might want to evaluate that to close it again. So now we have like a closed geometry there. So then you can just like print that because it's a solid, and then you can set actually the shelling thickness by the printer in the slicing algorithm. Let's look at another one. So that's an interesting one there. It's basically creating like it's like kind of like inner tube thing there, which is pretty interesting actually. And if you look at the geometry here, that was the box type, so that's what the geometry actually looks like. So we just bake that out, right? But then once we smoothed it, it became that kind of funnel geometry. And these things you can also use, like if you want it a bit sharper before the smoothing, you can use Weaverbird's constant quads, which will just give it more faces and then smooth it. And what that will do is, you see how it's like kind of more boxy now, and actually if I give it even more, right, so it just gets boxier and boxier, especially on the inside there, and especially on the top there. But I tend to like the smoother one. And this one probably, this will work fine. No, because there's a because there's an opening. There is actually an opening in the middle, so it just like closed that whole thing there. Funny. That we'll see examples in the next steps of where that kind of close is useful. So in this one, you can also do like the volumetric thickening. And notice in these cells, we're not adding any divisions in the Z direction because these cells aren't set up to connect in the Z direction because they're flat on the top. Although this one would connect. So you have to look at that too. Like if things, again, always just check it if you're unsure, like by just baking it and then like copying it up or to the side just to see, so that they would connect, right? Because there's edges shared there and they would be able to connect on top of each other. Whereas this one here wouldn't be able to, because if I copy this up, now you're going to have duplicate faces there because the top of that was flat. Unless there's a parameter in here which you can look at and explore that changes the angle of that, then it would work. So if I went back to this cell and then changed the Z, you're going to be able to start stacking that. Right? So now they're stacked. And actually I didn't want to do the closing there, because again, this isn't a kind of geometry that closing is really good for. Yeah. Okay, and you can, also, if you go back to our rig here, you can, also change things in the other direction as well. In, in each direction. So maybe you want more along that axis. You'll notice there's weird displays with Grasshopper in like Arctic and rendered. It's like cutting off half of it below the ground plane. So yeah, create something like that. And let's look at the last one here, which is called cross. Again, these are just all examples of different cell types that you can experiment with. Different spacings. Yeah, so that will give you like a lattice. Actually, this one should work with the closing system. So if I actually close this one up, you see how we close all those openings? And I'll just zoom into that. Yeah, so you got this nice interconnected closed geometry. And this stuff, like kind of weird stuff there, it's like really just display stuff. It goes away in like the proper rendering softwares. So next we'll look at creating our own, kind of our own examples of cell system and we'll look at using attractors to make some of the parameters variable, especially for these pre-made ones as well. Okay, so now I just want to show how we can make variable cells here. And what these variable cells will do will let us use different thicknesses for different twisted boxes based on some parameters. And I'll just show an example now with the IWPR because it has the capability of parameters that can change without changing our edge condition. So the first thing I'm going to do is actually want to just take our rig and group it so that we can know which part is our rig. And I just want to copy all of this into another file just to be consistent with the video so you can follow along so that the files are the same as the video we're working on. Now, I'll just delete these for now and we'll just look at this one. The reason I want to look at this one is because what we're looking for here is the naked edges. Remember, those are important for our connections and they need to be the same size in the same location for every cell so that they'll connect together. This particular component, and if you look at the other components, you just have to play with the parameters from Mesh Plus. The T is the parameter for the cell, and it's 0 to 1. But for instance, if you look at T0, that's not a parameter we want to change. You can change it once if you want your cell to be different, but we don't want to change that parameter like we don't want to make it variable for each cell because then they won't touch when they propagate and connect together. For instance, if I bake this and then did another one where I changed that and bake that one, you're going to have issues with connection. Okay, so you see how if I turn this off, so you have like a hole there, right? So the connection is broken. We don't want that. However, this component does have T2 and T3, which can change the shape of the geometry without changing, without changing the connection edges here. Okay, so what we can do is we'll get our twisted box. We have our twisted boxes here. That's these ones here. And what we'll do is we'll get the centers. So I have a component Pufferfish, twisted box centers. Right? And you have different types of centers. This is going to be the corner point center. So it's going to average the corner points and give you a quick center. And it's just something that we can measure to. And we're going to use an attractor. In this case, we'll just use a point. So we'll set one point somewhere, maybe there. And we'll do a pull point. Right. So the point search from, geometry that pulls is going to be our attractor, and that will give us distances. And what we'll do with those distances is we will reparameterize them, reparameterize numbers. We can use a graph. and we'll use those numbers as the input to change that T2 and T3. So I'll just plug that into actually we want to be careful not to go to 0, because if we look at this cell, when we go to 0 you get like a weird pinch point there. So we'll just remap it. We'll remap these numbers and we'll just give it a domain that doesn't reach 0. So we'll just do construct domain. And we can make that domain do something like, I don't know, we could do like 0.1 to 0.9. Okay. And then we'll use those values for T2 and T3. Okay, it seems value to new vertex. I think if I just, because it's list access, so what I should do is just graft it. Okay, so now what you've made is you've made 16 cells, because we have, in this case, 16 twisted boxes. Okay, and they're all going to look weird and overlapped there. If you bake them, you can pull each kind of one out in succession. And then what we're going to do is we're going to put, based on the attractor to those twisted boxes, is we're going to assign now those geometry to their respective twisted boxes. First, what we want to do is, since all the naked edges are the same and the geometry doesn't exceed the boundaries of those naked edges, we'll just get one of them. So we'll get one of the cells here, flatten that so that we can just get one. We only need one to generate the bounding box, right? Because we want a same bounding box for all of them. You could just plug them all into bounding box, but then that's just going to unnecessarily make a bunch of bounding boxes when we only really need one of them, because that one covers the size that we need for all of them. So this is just a way to generate one bounding box based on the naked edges. Okay, and since our twisted boxes are already as a list, and the output here is as a list, a grafted list here, you just plug those in, and now what you'll have, I'll get rid of that close there and turn this preview on, right? So now you'll have, if I could find my attractor point here, right? So there's my attractor point. So as I move this thing around, you'll see how the geometry changes, right? So actually, let me get a preview component so we can display it easy. Okay. Okay. So as I move that point around, here's like the more open ones up here, and of course the size is also based on twisted box, but you see it's like a kind of like an X shape here, whereas if we go down here, it's more like filled out and boxy shaped. Whereas if I put the attractor down here, it's going to be more X shaped down there and bigger and boxy shaped up there. Okay, so that's how you can use variables. But again, you want to make sure that those variables in your cell don't change the connecting edge. And if you want it, you can just do flip here, or you can do it here also. There's a flip if it happens to be the other direction. And I realize I have that off for some reason. There we go. And if you want to just flip it, just use the flip here, the F option in rebuild. And you'll have your gray faces for the most part outward. And everything's nice and connected. Okay, so what I'm going to do now is I'm going to copy this whole thing down just so I can keep this up here for you to use and look at. I'm just going to turn the previews off. And what we're going to do now is we're going to make our own cell that can be variable. So what we'll do is we'll start with a base box, which will be a center box. And we can actually, we can work like over here, and then we'll be connecting to these twisted boxes afterwards. So we have our center box, and it doesn't matter the size, but if you want to see it easier as you're working, you can just make it bigger, just so you don't lose it in the canvas. So we'll start with this box, and we will scale like the box and scale the edges of the box and construct a simple unit cell. So first we'll get the volume. Of the cell and scale the cell. Scale the box by the center by a factor. Okay, so you can see that box scaling in there, and we will deconstruct the BREP to get the faces, and then we'll get the edges of each face. And we'll join it so that we have each face's edges joined. Okay, so basically what we did was we scaled the box, got each face, and created a separate enclosed polyline for each face. So if I go and select that, you have each face there. And then what we're going to do is on the original box, we're going to also deconstruct that. We'll get the area of each face. We'll scale each face by its face center. And we're going to get another factor, which is going to represent the size of that face. And we'll do the same thing here. We'll get the edges and join. So what you'll have now is this inner set of edges and this outer set of edges. And we're going to weave those together so that they're in sets of 2. So you just graphed the inputs here, and I'll get my param viewer, right? So now each one is sets of 2, right? And a set of 2 is, if I just go here, I'll simplify the paths just so that my paths, I can call them as whatever, 5, 0, 1, 2, 3, 4, 5, and highlight it. So you can see now each one is paired together in its branch. Because they're paired together, we can then loft them, and what we'll use is Pufferfish's parameter mesh loft. Again, we want to stick with meshes here. We can smooth them. They're quicker to morph. Just easier to work with in this case, right? So there you go, right? Now parameter mesh loft uses UV parameters, and that's why if you look at this, it's not sticking. It's not sticking to the edges there. That's not good. So there is a special option in the parameter mesh loft. So again, UV would be, just like everything else in Pufferfish, range based. So U and V. If I display and turn on the mesh edges, you can see, so this is going to control the mesh edges in that direction, and this would control them in this direction. You see how they go around. So if I went to 4, it would work, right? To stick to that, to stay in that edge. But the parameter loft mesh has a special option, which is called, again, there's weighted like before from the curve examples, but has a special option called lengths. And what it says is if it's true, the section curve mesh face divisions are defined by the lengths between their control points instead of the U parameters. Okay, so if I turn that to true, so what's happening is instead of using the U parameters, so that's what the U parameters, which is default, there's 11 of them, and so you have 11 divisions around and it doesn't hit the corners. If you set it to true, it's going to say, okay, make a mesh face between each control point of the curves that I'm lofting. Okay, so there's 4 control points, it's making the face between each control point. And for this case, we just want one V, and there's an override for all Pufferfish components for parameters that you don't have to do this and do 1. You can actually just plug the number 1 in. And basically what that does is it makes it 0 to 1. It's just a little behind the scenes override of all the Pufferfish factors and parameters that you can do that. If you went lower than 1, you would be doing something like that, you see? Right? Because you're going like from 0 to 1 as a divisions. Or you can do that, which is giving you divisions between 0 and 1. So in this case, we just use 1. I'll just keep it like this for now. Actually, yeah, I just use this because, as I said before, like things I don't want to really change, I just use a panel. 1 and true. And that gives us all those lofts, and the only thing we have to do now is just flatten and join. bake, right? So if I bake that, you know, and then the lofts, the inside or outside direction is based on like the orientation of the curve. It's just the way that Rhino and Grasshopper makes mesh orientations that aren't solid. It kind of has to guess, and it usually goes by the orientation. But that's okay because, as we know, we can unify the normals. So let me just unpreview this. So now you have this cell, your simple cell, that you can control like this, right? And you want to set your factors so that you can't have that condition. So I'll usually go like values and I'll set the minimum to like 0.1. So I can't go, oops, set the wrong thing there. So values, we'll set the minimum to 0.1. And we'll set the maximum to 0.9. Because if I don't set the maximum, also you can get where these things connect like weird like that. So values maximum 0.9. Okay. And you can go lower, you can go like 0.001, 0.99, whatever. Just what I'm doing now. And we'll do the same for this inner one, because if we go all the way in, we're gonna just go to nothing. If we go all the way out, then when things connect, you're gonna connect to each other, you're gonna have duplicate faces, right? So we'll use the same 0.1 to 0.9 logic just to check ourselves and make sure we don't mess up here. Okay. So now you have this cell that you've made. What you do with that cell is just as we did before. Up here, you'll just morph to TwistedBox and weld and all that fun stuff. So we'll morph to TwistedBox. And I use this one, I think I mentioned it earlier, instead of the regular box morph, because the one I've made in Pufferfish morph to TwistedBox is multi-threaded. So it is actually a lot faster with a lot of meshes. However, it won't work in Rhino 5 because Rhino 5's spatial deforms weren't really thread safe. So you'll get a lot of, it'll go through, but you'll get a lot of weird looking geometry. It's something they fixed in Rhino 6, was making a lot of these things thread safe. So I'll now that we have our thing there, as always, we get the naked edges. And with the naked edges, what we'll do is get a bounding box. And make sure that you go to union box. You could just do it this way. I just like to use the edges just to be safe in case, as we'll see in later examples where we use different cells that are different sizes but have the same shared connection. So I just like to use the edges. In this case, the bounding box will look the same. That's our reference, our geometry will be that, and then our twisted boxes will be from our rig that we made. And we should actually, in this case, flatten. Then we go here. So get this preview here. And we'll want to weld this up also. So now that we've done that, we'll join all the cells together. Right now they're separate cells, they're 16 cells. Join them and then rebuild rebuild mesh, and we'll unify and we'll combine identical, and we'll do just as we did before a distance weld as well, just to take care of anything that might be a little off. And we can smooth this one as well if you'd like. Okay. Okay, so if I just turn off these edges, so there's your cell there, smooth and joined together with its normals uniform. We can check if it's outward, so it's the correct orientation that we want. Red is in, gray is out. And now you can go and change these parameters, and it will change there in your unit as well. This is the kind of geometry that will work well with the close, because there's nothing that can get confused about closing this inner circle where our finger should go. Again, you could thicken this also. This geometry wouldn't be hard to thicken because it's not as complex as the bat wing, where you have to worry about so many potential self-intersections. So you could thicken this one up pretty easily until down, see, the problem is down there, right? So you want to just be careful about that. And if you like that look, you can actually do that, and then when you do the volumetric smoothing, we can keep that geometry. Or we can smooth inward, thicken inward, and then try to avoid that. But then you have to just be careful about how thick you go inward, because you see at some point these little guys down here will start to come in on themselves, right? So thickening is always kind of like a weird issue that is better resolved with volumetric shelling and thickening, which we'll look at with Dendro and ZBrush, a ZBrush example. But for this one, what I'll do is I'll use our close mesh and just close up all the holes. So you'll see now all the holes got closed up and smooth. And there you go, right? So that's like the closed version of that, if you didn't want the holes there. So now we'll make a slight modification. We'll make a slight modification to this so that we can make it variable. So we'll just copy this whole thing down here. I'll turn off the preview of this one. And basically what we're going to do is we're going to make it variable for the, turn this off real quick. Okay, so we're going to make the cell which comes to this point, and I'll just disable this and just focus on the cell for now. So we'll add a few things to this so that we can do like we did with the mesh plus one, which is make it variable sizes. And the factor we're going to hook into is this factor here, which is this inward outward, get my mesh edges here, this inward outward factor, because again, we don't want this factor here to be variable because we need those connections to be the same for each cell. Okay, so that's the factor we'll be hooking into. So I'll just get a number parameter there. And we'll get a point, and again we'll base that. Actually, don't want to set it here. I want to set it here. Get a point and set one point. We'll set the point here, and it's going to be just like before. It's going to be relative to our rig. So we want to take these twisted boxes, and we want to do again twisted box centers. Twisted box centers. We'll bring that down here. And with those centers, we'll measure the closest point by using, again, pole point. And we will we'll remap it. We'll get the bounds, so we know the starting bounds. We'll use remap in this case instead of reparameterize because we want to use a different target domain. It's not 0 to 1 for the same issues as before. We don't want to go 0 or 1 because it can create overlap faces or pinch points to nothing. So we'll do construct domain. Just get this. We'll make it 0.1 to 0.9. And that will be our number. Okay. And the other thing we need to change, you'll see like there's some stuff going on here. What we need to do here is we need, if you look at these join curves, right, they're, if you look at the paths, there's kind of a group of, you know, there's this one here, and then there's the next one. This is just tree stuff. If you don't understand it, you should look into like some tree and data stuff from the online or manuals, maybe list examples. But you can see there are different sets there, and that's the sets per cell. So we just shift the paths. So shift paths. And by shifting them, we now have, you know, we have them, sorry, and we should simplify also. There we go. So that you have the six sides per branch for each cell. And I will just, for the timing, sometimes if you plug the wrong stuff into this weave, you can calculate too much stuff. So plug that in there. But the next change we need to make is we need to make these lists equal each other in terms of structure. Right now they don't. So what we'll do here is we'll take these curves, these outer curves, which are our connection curves. We'll duplicate them. With the repeat, actually, we can use repeat data. And we want to repeat this data the amount of twisted boxes that we have. So we'll get a list length. And our twisted boxes are here. Okay, so now we have, we have now like the same kind of structure as before. And what we want to do is flip matrix and simplify. And once you, sorry, what I missed here is the list length. It should be flattened, right? Because we want to measure how many twisted box. It was graphed up there, right? So flatten that. So now you have the same amount, you have the same structure, right? And since we have the same structure, you have each cell's 6 sides, outside each cell's 6 connectors here. What you can do is just move this out a bit here, is then use these here. Okay, so we weaved, and now we have our pairs for lofting, our edge pairs. So it's important to always evaluate your data, and if you don't understand this stuff, it's the hardest part of Grasshopper to learn, is understanding how these lists work. And it's not something we can teach in a short video. It just takes practice and studying. But yeah, always evaluate how that's working. So now that we have that, the other thing we need to add is here, we don't want to flatten. Instead, what we want to do is we want to shift the paths. Okay, so we should end up with the same structure as these for our lofts, because we shifted the path. Before shifting, it looks like that, right? So this is one cell's faces, and then where that first number changes, that's the next cell's faces. So you're looking at these 1, 1, 1, and then 2, 2, 2, but we want them to be together per cell, so we shift the path. And then once we shift the paths, we join them. And like before, when we have multiple cells, so again, I'm just crawling through and looking at the information that we're getting. So we have all of our cells there, our 16 cells. We just need one of them, like before, to get the bounding box. So flatten, and then just get one of them, the first one there. That will give us our bounding box that we want to use for all of this. And then we're going to be taking all those cells, and we don't want to flatten this time, because we want the 16 cells to go to the 16, if we go up here, the 16 twisted boxes. So I'll just enable that. So now, if I move this point, am I looking at something wrong here? Just preview this. Ah, yes. So then this needs to flatten, and you have your connection there. And then as I move this point around, just bake this real quick. Actually, I want to bake the joined one. And seems that the size didn't change, and that would be, what am I seeing here that's in my way? Just trying to look, see, I know I did something incorrectly here. Let's see. That is because the distance, all those distances, bounds. Because I forgot to flatten the bounds. See, stupid mistakes like that. But I'll leave this stuff in the video because I want you to see kind of troubleshooting and oversights that can happen. So you have to flatten that bounds, because basically what was happening is, because it was grafted, it was giving me too many items in my tree here. Okay, so now if we go here, there we go. That's what we're looking for. So I'll just turn off the mesh edges. Okay. So yeah, I mean, even when you're experienced just kind of doing this stuff really on the fly that I'm doing here, you can make oversights like that. But it's important to see them, so I'll just leave them in here so that's, you can know what kind of things to look for. So as you see, as I move this point around, we change the type of cell because of the way that that we're changing those sizes. So that's it for this this portion, and then next we'll be looking at a few different ways that I like to make some cells, both manually and parametrically, and a mix. So in the what I wanted to remind you also is, as we made this thing in the past video, you can also go through and change the settings on your rig to, adjust this thing to give it as many kind of divisions, and you'll get, various different looks from it based on, based on your divisions and your attractor's location. So if I do like more divisions in the Z direction, let's say, right? And if you go all the way back to the beginning where you had those divisions around, you can get some interesting results. Yeah, so you can get stuff like that, right? So you get like these bigger pyramid kind of shapes. This is just like some of the stuff I was working with. Or you can have more divisions, but just make sure that if you want it to look a bit different, just play with this graph here. So you can get like a big, if you want like a bigger spike there. Again, the important thing is that we don't intersect that ring. And you can play again with all of your settings here. So if you wanted it thinner up top there. And if we move our attractor point, we'll change the type of inflation kind of on this. Now those are like the big inflated ones up there. Down here, they're the less inflated ones. And vice versa. Okay, so that's just something I wanted to remind you of, is to just play with those settings, play with the divisions, and you can get a pretty unique design. It's updating a bit slow because of the smoothing. You can turn off all like the smoothing layers. I have it pretty high on like the Catmull Clark right now, so that's why it's taking a bit of time. So as you're adjusting things, you'll just want to like see that's what's taking the most time, is that Catmull Clark. So you can just bring that down to like 1, and you'll see a dramatic kind of improvement there. And then once you got kind of a system that you like, then you would smooth it again. So now we'll move on to the next part, which will start making some cells, both parametrically and manually. And then what we'll do is we'll bake the cells, and then we'll edit them manually, and then we'll tween between them to get variable types of cells, and then we'll propagate them into our rig. So for now, I'm just going to go to a new file, and the first kind of cell we're going to make is going to start with a rectangle. You can just zoom into it there, and again, the cell size doesn't matter, so I just tend to make it big just so that I can see it easy. So we have a rectangle there, and we'll get the center, polygon center, faster than using area. So I tend to use that a lot if it's not a curved surface. And then what we're going to do is we're going to scale that rectangle a bunch of times. So we'll get scale. And the geometry, actually we'll make a compound because we're going to do we're going to do scale and move. And what you can do when you have multiple transforms is you can compound them, and it's faster. So you wouldn't put anything in geometry for now. Right now we're just going to make the transformation data, and what we'll do is we'll get a gene pool. And gene pools are nice because it's basically like a collection of sliders. It's just so we can edit things, manually as we like the sizes. And for now, I'm just gonna double click it, and I'm gonna set it to 5 for the gene count. And I'm gonna set the maximum to 1, and the minimum, actually set the maximum to 0.9. Again, we'll do our, just so we don't go to 0 or 1, for reasons we discussed earlier. Right, so we have these 5 sliders here now. And we'll get a 0. I'll just put a 1.0. And that's so that we have one that is the same size as the rectangle, because you'll see we'll be lofting down to that same size rectangle in the list. So we just want to make sure that there is one rectangle that stays true to the size. So we'll just put the 1 in F first, then shift and put the gene pool in. Okay. And then we'll make a move transform. And for move, we're going to move in the Z direction. And we will edit this. For this, it doesn't matter. Like the movement can go to 0, and it can go to I don't know, however high we want to make this thing. We can use like 5, 10, whatever. Right, and then this will be 0. The reason we want 0 in this case is because we want one rectangle that is basically we're saying we want one rectangle that is true to the original size and doesn't move, right? So it'll be 0 first. So what we'll do is actually you plug that 0 into Z first and then the gene pool list. Now what we want to do is we want to weave the scales and moves together so that we can create compound transformations from them. So we'll just graft our inputs here. Right? So now you have these couples of a scale and a move in succession. And what we'll do with that is, since they're in 2 per branch, we can compound each branch. So it's called compound. It's a compound transformation. And then we'll transform. So we'll transform. And we'll transform the rectangle by those compound transformations. So what that does is, and I'll just flatten the output, what that does is it lets us create, transforms are not expensive to create computationally. So when you can combine them, it's easier. Rather than transforming the rectangle by scale and then transform by move, you can do it all at once by compounding and transforming. It just saves computation time. So then what we can do is we can move this this around to get our different scales here. You can see the scales are happening there. I'm just going to turn this off because that plane is bothering me. And then the moves, we'll do like a move like that, right? So we basically created this pyramid of kind of scaled and moved rectangles. So the next thing what we'll do is we'll loft those together. So we'll get the parameter mesh loft. Right, and remember from before how it's not touching the corners. The way we override that, is by using the length message, which says, use the lengths between the control points as the face divisions instead of the U parameters. So get the Boolean toggle and put it in lengths. So now we snap everything to those profiles that we made, those rectangles. And we'll want to use just one face in the V directions, right? So 1. Again, it's not division, it's by parameter, but because when we put 1 into U or V, it's basically telling U or V to be 0 to 1. It's just a little hack there. Okay, and then another thing we can do is we can close up the top of that pyramid in the same component by here you have a start point and an end point, and that's like an optional start point and end point for lofting, which can also use which you can see it says can also be used to cap the end of a mesh loft which has a closed end section curve, which we do have in this case. So we'll do a list item, and we'll go zoom in, and here -1 will be the last item in the list. We'll get the center of that last item. So now we have a point there at the top, and we'll just use that point as the end, and now you see it's closed it up, right? So now it's a closed up loft up there, okay, by using that endpoint. The parameter mesh components are have like a lot of really nice features to check out. And then the other thing that we'll do now is we're going to create a base for this thing, and then we'll loft between this geometry we just created to the base to finish our cell. So to create the base, what we'll do is we have our list item 1 here, which is the bottom curve. We'll explode that. And we'll get list item. And there's going to be 4, right? There's going to be 4 line segments there. 1, 2, 3, right? So that's our 4 line segments there. And we're going to move the first, the 0, I, and 2, we'll move them down and create a mesh from them, okay? So we'll get move, not that one, move, we get 2 of them, Z, and we're going to go negative, and we'll just get a slider to whatever. Okay, and actually 2 should be in this move here, right? So now you have those two lines down there that have moved down. Okay, so that's kind of be like kind of the base thickness of the cell, and you'll just merge those. And we'll again use a parameter loft mesh. So I'll just copy it, but this time we don't want to use an endpoint. But we do want to use the true for the lengths of divisions, and we want to use 1 for V division. And actually, because the winding direction of that bottom, we need to flip one of these curves. So we'll just flip 2 here. Okay. So we'll just get that down there. Okay, so that's going to be like the base there. And we'll get the naked boundary of the base and the naked boundary of the top part, and we will create a loft. We'll create a system through it to create the part of our cell which will be the connections between, when we propagate this thing into those boxes, it'll be the parts that connect to each other. So we'll get the Weaverbird naked boundaries, and we'll get the naked boundary of this here, and we'll get the naked boundary of our parameter loft mesh. Okay. So now that you have those two naked boundaries, you'll want to first plug them into another parameter mesh loft. And we'll want to flatten the input so that they'll be together, and we'll plug them in like that. Okay. So what we've created there, and again I copied it so that we're using the V as one division and true for the lengths division count in V mode. So now you have that kind of mesh that's around like that. What we'll do now is we'll get the face boundaries of this mesh here. So now you see I have the boundaries of all that face. We'll scale it non-uniformly, so scale NU. And we're gonna scale it by we're gonna scale it by the area point here of this one here. So let's say scale. Center. We want to get the center point of this naked boundary. So we have now that point underneath there. That's going to be our plane for the scale NU. And we'll just get a slider here. And we'll use that only for X and Y. We don't want to scale in Z. Okay. So we're basically scaling like outward of those faces, you see. You don't want to scale in, so better to keep it out. As a check, you can set the minimum to 1, and I'll just set the maximum to like 3, right? So that you don't go lower than 1. Okay. So then what we'll do is we'll get the center of each of those faces. So again, polygon centers. So now we have the center point of each of those faces. And we'll scale those faces. So scale the faces by the centers, and then the factor is up to you. Okay, so you see how we're scaling those faces there. Then we want to weave graft both inputs, and we want to weave the face boundaries, these original face boundaries to these new scaled face boundaries, so that they're coupled. Okay, see, so each branch has 2, they're coupled together. And then we're going to get, again, a loft, a parameter mesh loft. Like that. And we want to make sure we don't flatten, because if we flatten, you're going to try to loft all of them together. See how the list there is all 8? We want them to stay in their couples. Okay. So now you have that outside kind of connector rim there, and this one we just use, this one here we just use as a way to construct this one, so that one you just on preview, and that's kind of like what the cell will look like. Okay. And then you want to join all the pieces together that you need to make the cell. So we'll just get a mesh parameter, we'll just get a join, mesh join, and we'll plug in. So what we want is we want this mesh here, this top mesh that we made into there. We want this mesh here, which is our bottom mesh. So hold shift and plug that in, and we want this mesh here, which is our connection meshes. There. We'll flatten that input, and everything will join together, and now you have one mesh. So I'll just turn off the preview of all that stuff, and there's your cell there. And you can go through and you can, edit, the way that this thing is shaped. And what we'll do after we make another cell, we'll do like another twist on this one and then another one, and what we'll do is we'll bake them out and modify them manually so we have some differentiation and then between meshes there. So this is our this is one of our cells here. And what I like to do is, like, you see how that normal is weird, like, so we just do I'll just do rebuild mesh from Pufferfish and just do a bunch of the stuff that we were doing before, which is like just welding it, unifying the normals, combining identical, and we'll weld it just in case anything's a little bit off. Bake it, and you'll see, so sometimes, the unified normals kind of has its own mind, and it just cares about getting the normals uniform, but doesn't necessarily put it in the right orientation. You can just flip it in Rhino, or just use the flip from here if it is in direction you don't want. This F input here will flip it. So there's, that's the kind of cell we just made there. Okay, so that's one of the cells. Now we'll do a little twist on that cell. So what I'm going to do is I'm going to copy this whole thing down, and I'll turn off this preview here, and we'll just make some slight modifications to do a cell that is open on both the bottom and the top. So the first thing we have to do is we need to not close this top, because in this cell what we want to happen is we want a cell that can be repeated vertically as well. So we need a connection on the top, and we'll need to make one on the bottom. So we'll just get rid of this here. So we're just not going to use a cap point there. And you'll see it looks a little bit weird, right? That's because it's at this point here, if you remember, we found the naked edges. If I actually go back to this one, what we did here was we found the naked edges here, and there was only one, so that was like the bottom and then the naked edge there. So there was only one, so it knew to loft those two. But since we've opened it up here now, it gets confused because now there's two here, so it's like lofting 1 and 2, and then lofting down to this one 3. Okay, so in order to prevent that, we just need to implement something in this space here, which basically just says, okay, we have the two naked edges. Let's get the center points of each of those. Let's deconstruct them. and we'll sort the basically sort the polylines by z direction. So sort z k, and so we'll sort z, and then we'll sort the polylines, which is a, by z, and then list item a into L. So we're getting the polylines there, and so now we've just basically said, okay, let's take the lowest naked edge and only use that one this time. So we'll plug that in, and then this boundary, right? So now we have our thing there, but this time it's open at the top. And now what we'll do to make it open at the bottom is we'll use Pufferfish mirror cut to simply just mirror cut this into like a symmetry in the Z direction. So we'll get the mesh mirror cut, or mirror cut mesh as I've named it. And we'll need a mirror plane, and what we'll use for that plane is the XY plane. But we want to move the XY plane, because right now if I did just use the XY plane, it's going to, if I turn this off here, this one, it's going to get rid of our connectors because the connectors end at XY there. So you get this kind of shape like this. You could use this geometry if your intent was only to do vertical connections, but right now we don't have our side connections. So what we need to do is we need to move this plane in the Z direction, negative Z, by some number. And that's the plane we'll use. Okay, so now you can even create, so now you just do this, and you just want it so that they touch. You see how they intersect there, right? So now you have your little, now you have a symmetrical cell there. And I use connection type 2, which is shrink faces. Tends to just be cleaner for the most part. Actually, no, don't use 2, because 2 will get it. This goes back, so it's not good. We can just leave it at 0. 0 or 3. They seem to be the same. In this case, I'll just use 0. Okay, so if I go and bake that, now you got your, now you have your, sorry, I had to bake the plane there. So I'll just put a mesh output here, just like that. Yeah. I'll put one up here too. Okay, so now you have a cell here that is symmetrical, right? Because of that mirror cut. Okay, so that's another type of twist on that cell. The other thing we can do, another kind of twist we can do on this cell, another simple one. So I'll copy this first one down. And what we're going to do is we're just going to change that beginning part here with these pink, with the gene pools, and we'll just use ranges with graph mappers to change this cell a bit. So I'm going to get rid of all this here. Actually, no, keep the move. Get rid of those. And I'm just going to get a range. And I'm going to construct a domain. And I'll just get a 0 to 1 sliders. And with that, we'll get a graph mapper. Plug that into F, graph type. We'll just use Bezier for now. Do something like that. And then we'll get another range here. And we should set actually the number of elements. Maybe we want more than that, so I'll just go like 20, whatever. And just set it something like 10. And we'll use another graph mapper for the move. Just want to give this some room here. So for the move, we can use something like a sine wave. So I'll get another graph mapper. I'll turn it into a sine wave. Something like that, let's say. And then we will remap. And we'll construct a domain to remap to. And we will use these values for the z direction. So if I go over here and turn this on, okay, so what we've done here is we've created this kind of wave type topology of this. And it doesn't look substantial now, but it will be when we use it, because what we're going to do is, when we get to the next part, is we're going to morph these based on these out, just on the connections. So the bounding box is going to be the connections, and then everything out of that would stick out of the bounding box, which would also stick out of the twisted box. And this kind of stuff can look really cool once you smoothed it. So the next type of cell I want to make, there's two of them, and I usually make them. I usually make it manually. So sometimes I like to make this stuff, manually as well. So we'll just go into Rhino for now. Okay, so we'll just go into Rhino for now, and we'll make a. Just want to turn some stuff off and get some stuff out of the way here. Okay. So next one, in Rhino, I'll just change Grasshopper a bit here. First I'll do something like I'll make a rectangle here. I'll hold Shift, and I'll just get a rectangle like that. Okay. Then what I'll do is I'll start to like break down this rectangle, and I'll build with the single mesh face. Okay. So what I'm going to build actually is, first what I do is I just take a line and I'll like just divide this up like that, let's say. And then the important thing when doing something like what I'm doing now is that you always want to be symmetrical. So if I draw a line, if I put a point here, what I want to do is I want to mirror that point across this diagonal axis, right? So that I can get a line like that, let's say, okay? And then I will mirror that along this diagonal, okay? So now I have something like that. And then I'll build this out basically with a mesh faces. So first I'll connect across here. Again, I'm just building a frame just so that I can kind of like a guide. Somewhere you can go like somewhere here, let's say, and make sure that your perpendiculars snap is on, and you can just like that, and then mirror this one now across there. And now that you have that frame, you can go through with your mesh tools and get a single mesh face, which the command is 3D face. And then what I do is I just draw. So I'll put a face here, put a face here, and don't worry about the normal directions, we'll fix that. And then I put a face here, and a face here. Each one is a quad. We can flip this one, and then we can mirror these two across from the center across this axis. So then you just join these together, then press F10 or point on to take the points, and we want to take these points and lift them up. So you get like a bridge like that, okay? Then we're going to copy this in place. So copy in place and rotate it 90 so that you have like an X shape like that. But then you want to take this one and in the right side, right or left, you want to mirror it below, okay? So what you should end up with, and I'll just delete that one like that, and then you want to flip this. So what you'll end up with is a cell like that, right? So it's like it's a weaving cell basically, and then you can you can join these even though they're not touching if you just do join. So then it will be one mesh. So that's like the cell we just made, which is going to be this weaving type of cell. Normals facing the same direction. And the other thing, I do two of these. You could do one like this. And the other thing, the other way I do it is I'll just copy these over to the side here. And I'll copy them down. This is so you can create a thickness. It's easier than making the thickness afterwards with the thickness component. You just copy these down like this, right? And then in that case, what you'd want to do is you'd want to flip this bottom one and flip this one. You're basically creating two shells, right? And you'll just want to close it up. And you can close that up again, just quickly go around and close it up with mesh faces, quads. Make sure your vertex snap is on so that you can snap to these vertices easily. And again, you could probably do this also parametrically, but sometimes I just feel it's easier to do things manually. I like to do a manual and parametric workflow. And then I'll just I could do uniform normals after I join, but I like to just flip them beforehand so that grays are always out. Okay, so that looks good, and we'll join that up. So I'll select all that and join, and I'll select these two and join those together. So basically what happens now is now you have this cell that, if, for instance, if I copy it, it can propagate into a weave. You see, and the connections always meet, right? And you have this kind of weaving. And so you have the no thickness one and the thickness one. And so next, actually I will put these in here at the bottom here. So let me just put this set one mesh, and same with this one, set one mesh. Actually, I'll put them above that, and I will just internalize them so that they're in the file. Internalize, okay. Okay, so next we'll look at propagating these cells we've made and also editing them and blending between them to get variable types of cells on the TwistedBox rig that we've made. Okay, so now what we'll do is we'll bake these cells that we made and put them into a new file, and then we'll look at propagating them and tweening different versions of them by editing them. So I'm going to just go to my rebuild mesh, the first one up here. I'll bake that out. The location doesn't matter, so I'll just put it over there. Same with this one, bake it and just put it somewhere over there. And these two, sorry, we have one more here. Bake this one out. And these two I'll also move. Okay, and actually these two here, I want to weld them first. So I'm just going to go into the new file, just open a new file, and I'm just going to get a few mesh components here. One, two, three, four, 5 of them. And I'll just set these in to this file. And like I said, with these two, I'm just gonna weld them real quick, just to make sure they're all cleaned up. Because I didn't have a weld because we built those ones manually. So we'll unify, combine identical, unify, combine identical, and we will weld them both. And I'll just hide these so they're out of the way, and I'll bake these ones. And I'll just get rid of this. I'll just move these over to the side real quick, and I will show the original ones and delete them. And I'll put these back into these containers here. Okay, so And then I'll just internalize these for the file. Okay, so all of our meshes are there. And the other piece that I want to get is, just move these down for now, is I want to get our rig. So from whatever file that you have your rig, just take this here and paste it in. And I'll display our rig and get rid of these curves here also. Okay, so the first thing we can look at is morphing those in. So we'll get the morph to TwistedBox. Twisted boxes will be that, and then we could flatten it in this case. And then the geometry will be whichever one of these that you want to look at first. And then the important thing here is going to be the bounding box. In this case, since if you just want to morph that one cell around without like blending or changing size or anything like that, you can just do a bounding box around that geometry and use that as the reference box. Okay. So one thing to know also is you see how they're all kind of inside of what I actually wanted them to be. Sometimes it's based on the direction of the curve that these TwistedBox are created, orientation of meshes. So sometimes you just have to rotate those things. So in this case, we can just rotate on the XZ plane. We'll just get from the bounding box we'll get a volume, we'll get the center of the bounding box, and we'll make an XZ plane there, and we'll use that plane as the rotation, and we will just rotate the mesh, and we'll put it to degrees, and we'll set it to 180. Okay, so what that did, if I just hide this, is just flipped it upside down, right? So now it's just the other direction inside that box. And we'll just use that geometry. Okay, so now it's the orientation that I kind of anticipated it should be. Okay, and what you can do is sorry, just looking at something real quick. And yeah, so I'll just turn that off. But what we'll want to do is when we create multiple of these, maybe we want like one to be more taller than the other and then blend through, is we'll want to look at those naked edges only. right? So we just want to do a bounding box. So that means we should put this to union, and we just want to do a bounding box around that. And that means you're going to get this really big thing like this, right? Because now your bounding box here is only around the connection pieces. Okay, so you have this really big thing like that, but it ensures that the connections always touch. So what you would do in this case is you would just make these much smaller. To accommodate that. So you make your twisted boxes smaller and just say that, like, okay, my twisted boxes equal the connection, not the overall geometry height. Okay. And then you can go and add more of these if you want. In this case, we shouldn't do this direction because these don't have a connection on top. And also, because we're only looking at an outer edge condition for the naked edges, they're going to go into each other. So we just want one for this one. And we can play with the amount of pieces as well. I'll do something weird like that. And then what we can do is close up those naked parts on the on the outside there. But first, we will join the mesh. We will rebuild the mesh to weld it and unify it. And then we can close it. And then we can smooth it. Okay. And yeah, so then you get something like that. And then if you want it to be even like we looked at before, if you want like a sharper geometry, you can look at also the constant quads subdivision first, which will give it more quad faces without smoothing it, and then smooth it. Right, so now you have like a harder edge there. And you can even bring this to like 1 and bring this to 2. Right, so there's like a harder edge geometry if you wanted something like that. So if I go and bake this, see, and it's all connected within and all that fun stuff. So now we can look at like the other geometry types as well. That was that one that we made there. We can look at the, like for instance, this one here. I'm just going to put like another mesh thing so it's easier to plug things in and out of. Okay. Or this one here. All right, so this one will go in because this one has naked edges at the top and bottom as well. So when we test a bounded box against naked edges, it does do that bounding box. So in this one, you might want to change the, the height of this back to a higher geometry if it's the desired kind of look that you're going for. And remember, we have this attractor here too, this point on curve that travels around our rig, so you can do different small or big adjustments. And this one, because it has a top and bottom connection, the mirror cut one we made, you can also layer this one in the Z direction. So if I did like 2 in the Z direction, you'll see how it's connected there in the middle, right? Because it has a top and bottom connection. So if I do the smooth version of that, let's bake that one. And I'll go to Arctic, let's say. See? And they connect there in the middle. So again, all just adjustments depending on like really what the look that you're going for is. So then we can look at this one, which was like a wavy kind of thing that we did. And again, this one only has the edge connections, so it's gonna get big. Like it's gonna get really big because it's only the connections. And also for this one, if it doesn't have top and bottom connections, you want to do 1 division. All right, we're gonna get something like that. Right, so only the connections are paying attention to the twisted box space, and then these come out of the twisted box. So always pay attention to what kind of open naked edge connections you have to determine your Z divisions and also the height of your twisted boxes in certain areas. So this one might look cool like if we only smoothed it. You get something like that. A little thin, but you just have to adjust the kind of angle and the height of your twisted boxes. For now, just kind of just showing you how the different cells work and go through. But yeah, you would just adjust the angles and all that just to get the thickness and everything that you want. And this one might look good like if you just did 1 of these, let's say. So you kind of just mix and match to get the smoothing amount that you want. So this is like more rigid, more square shaped. And so we can look at now this one here, which was our no thickness weave. And the weave we shouldn't close it. it doesn't need to close. So for the weaving, we'll get rid of the close. That's why it was looking weird. There's your weave, your connected weave. So just plug this into the Catmull Clark directly. And you get this kind of ribbon. You just bake this out. Yeah, so now you have this ribbon. And with the one-dimensional one, you can do like a thicken. So you give it a thickness, and then you can do that. But do you see how the thickness can get a little bit weird, especially in like there. Might also just be part of the, yeah. That's why I don't really use the thickness so much. But if it's just for like visualization purposes, it's fine. You see, like that looks pretty interesting. But then you have like this weird stuff there because it was like too thick, the thickness we're using, and it started self-intersecting with things. And that's why I prefer to make the thickness in the cell so I won't use that thickness there. And I'll use this cell here with the thickness. Something is weird there. I think it has something to do with the, let's see. Oh yeah, because this thing is just like way too big. Because again, it's looking at those connections and then making the twisted box from those connections. Whereas with this one, it was making the box, because that's all naked, it's making the full twisted box. Here, it's just looking at those connections again, so it was going like really far out. You could, in this case, because if you don't blend it, you can just use the twist. You can bypass the naked edges. Let me look at it. Yeah, right. Okay. And this one, since it does have a thickness, you can use this close to close it up. And you'll see it's just like a much nicer way because you avoid all those self intersections that can happen by thickening a mesh afterwards. Okay. So everything's nice and thickened and not self intersecting. But if we want to use these edges like before, we just have to make sure that our boxes aren't so deep. something like that. Because they're going to come out of the boxes, because those boxes are now just looking at the connections. So really important to know what kind of unit you're using and what the connection type is. Okay. So what I'll do now is we'll just turn this off, and I'll copy this. I'll copy this all down. Here. Save this. And I just want to bake these and set them in again. And we'll actually look at one for now, like for instance this one here. What I do is first, yeah, I'll just do it for one of them, and then you can go along and do the same principle for basically any of these cells. You can do this principle, which will be you take the cell, we'll just copy it over. Important to copy the cell because you want to make sure you never change the cell's topology so that we can blend them properly. And then what you'll do is you'll just turn the points on here. Make sure you do not change these points, which will be our connections. Otherwise things won't connect properly. And you can go through and we can start like playing with this thing. Like maybe we want this one to be like fatter outwards like that. Maybe we want this one to have like a dip in it. Go down, something like that. And see, now you'll see that there are different heights now. And you can even make it like asymmetrical if you wanted. Do like all kinds of, you could just do, different kinds of stuff to it. Might look weird. For now, I'll just stay symmetrical. You also want to make sure not to go outside in the top view of those connections, because then you're going to have intersections. So let's just say that's like our two cells. What you would do then is you want to move this cell back here, so they should exactly overlap each other so that the connections are the same. And we'll get our meshes. So we'll make this one this inner mesh, this first mesh. And we'll make this one this second mesh. Okay. And we'll basically then blend between them, similar to what we did in a previous exercise with a cell that we built. So we'll measure first, we'll get the TwistedBox centers. So those are the centers of our boxes we're going to morph into there. And I'll just change this for now to 1 so we can just visualize it easier. And we'll do a pull point. And our geometry, we can use an attractor. In this case, I'll just use a point like we did before. So I'll set the point. bring these meshes over here just so I can use them easier. And we will reparameterize the number. So there's 0 to 1. We get a graph. And then we'll get a tween through meshes. You can use tween too also, but I don't know, I like to use the tween through and just plug them both in. Mesh, so we'll put this mesh and this mesh. And the factor will be these factors here. And we need to put this point into our attractor geometry. So you'll see here, we're going to have all these kind of, if I bake that, you'll have all the versions of blending from one to the next based on how many twisted boxes you have. And if I actually, we don't want to separate them because we just want to do one bounding box. But if I actually did separate them just now, just to show you, you see that's the tweens there. Okay. But we want them overlapped so that we only have to calculate the bounding box once. And the way we did that before, if you remember, is we just take one of those, we get the naked edges of it, and we get the bounding box of that. Make sure to put it to union box. So now you have a bounding box around that system there. So we only calculate it once. And then we'll morph to TwistedBox, the Pufferfish version. And the geometries will morph are from the tween. Reference box will be this one box here. And then the twisted boxes here, they're not flattened here, but we could actually just flatten it here in this case. The important thing is that, so we have 11 twisted boxes and 11 geometries. And they're facing inward again, as you know, we remember we had that thing, we had to like rotate it around. In this case, you can just also do it in Rhino, just turn them upside down. Easier for this in this specific example. But now you'll see, based on our attractor point, I'll get a preview here. And put this on. So now, based on our attractor point, so here's the ones with the holes in them, and then like down here is the ones without the holes in them, and then it like blends between to them, right? So if I put this here, now you have those ones without the kind of indent in it, and here you have the ones with the indent in it. And you can go through and change this geometry at any time, as long as you don't change the topology, which is the amount of vertices and the order of the vertices, or the connections, it will work. Okay, and then so then you can go ahead and you can add more of these if you wanted. Maybe you want more around like that. So now if I go ahead and do our usual system here, which is where we join mesh, and rebuild the mesh, and Boolean toggle, get that uniform, and weld it. Then you can do stuff like smoothing and basically everything that we were doing up here. If it's something with holes in it, you can close the holes. In this case, it's not. You can do a constant quads. You can do a Catmull-Clark, a thicken. So just put this here. Put this here. Plug this in here. Okay. And actually, in this case, I do want to close it because there's openings on the edge condition. So we'll get that closed first. Just to close up that edge. And I'll bake this. And there you go. So now you'll see at some point it's like the indentations are there, and then on this edge, because of the attractor, they go away, and then it slowly starts to fade into like a bigger indentation there, which is, has a quite nice effect. So that's like a way I like to work both parametrically and manually at the same time, kind of back and forth. And you'll see here it's like a mess because for some reason Arctic and rendered views in Rhino 6, even though the preview is not displayed on other stuff, it still shows, so you gotta like disable them. And that will also work for instance, like stuff like this here. And you could do it with this you can do it with this thick one too. Yeah. So I'll just copy this down again real quick. And what I'll do is I'll take this cell here, again, copy it over, and turn on the points, and you can do something like, I don't know, maybe just take these points. Again, you don't want to change anything on the edge condition. So I'll just like scale these inward so they get like skinny there. So they'll become like more, oh, I missed a vertex there. So I'll just scale them inward. Okay. So now you have this like thinner one and this thicker one. And then you'll just move this again, move it back to where it goes so that the connections are the same. And even though these aren't touching, there's still one, this is one mesh and this is another mesh. So if I go here, I'll just turn that off for now. And I'll turn that off for now. We'll set this one here and this one here, if we look at the tween, if we just preview that, you see it's like tweening from one to the other. So if I just bring this really easy, so it's going to make that thickness, from the thicker to the thinner to the thinner. That's just so you can see what's happening, but they should be on top of each other, just as we did before. And all those tweens will happen, over, or on top of each other there. And again, we need to turn that off. Turn this on. So you have this kind of thing here. And come here, put this one on. Yep, cool. So I'll just bake that. Arctic here. And you'll see it's like got the, it's actually a pretty interesting one. It's got like the thicker thickness there, and then the ones down here where the attractor were are that thinner thickness. This one also, you can, if you change the orientation of them, that orientation also will change. See, that one didn't work, right? Because now the connections wouldn't connect with each other. So, yeah. Just by changing the orientation, you can get a different, I'm just rotating these cells here, get a different kind of patterns. And you can then, if you want, I don't know, you can have more in this direction, something like that. So you start to get some really interesting stuff by doing this. So I suggest that you look at these cells and play with them and start to create your own cells, and just what I did there, you just manipulate them in a way that you change some vertices and stuff, but always make sure to keep the connections the same on both cells, and the connections in the same location in Rhino overlapped in both cells. So next we'll look at some thickening techniques for some types of designs which might have overlaps. Okay, so in the last part of this webinar series, I just want to talk about thickening and kind of just finishing preparing the final product. And we'll look at a way with Dendro and then a way with ZBrush. I prefer ZBrush just because it's faster and, in my opinion, makes a cleaner mesh geometry. But if you don't have access to ZBrush, you could use Dendro or some other way that you might find. There's also some free softwares like Mesh Lab, stuff like that. That's I don't use often, but in my opinion, might as well use the kind of easiest and right tool for the job, which doesn't always mean Rhino Grasshopper. So I have this ring here that I've already pre-made, and I'll attach this file if you want to look at it. and I'll just turn to rendered mode. It has thickness, as you see there. The issue is that, for one, there's some slight overlaps here, right? In this zone here, things are actually intersecting each other. And you can see it a lot down here too. Like all this stuff here is intersecting. If I actually go back to shaded and look at the wireframe, you can see kind of like all that junk there. And if I got like a clipping plane and just looked at the section of that, so you see like all that there. That's not good, especially if you want to be like 3D printing this. There's some slicers that can handle that, but for the most part, you want to try to take care of that beforehand, and that's where we come with the idea of like shelling instead of thickening, or volumetric thickening. So just a different kind of concept. So let me just get rid of this clipping plane. Just move it over there or something. Okay, so we'll look at Dendro for this. Let's see, where is Dendro in my menu here? There it is, Dendro. So Dendro is a volumetric modeler that's using the meshers, the same mesher that Houdini uses, yeah. So to get that work, just make sure it's in the installation instructions, but just make sure go to Grasshopper developer settings, and you have to turn off. This is on by default. You have to turn that off, or else Dendro won't load. So turn off the memory load. Okay. So first thing we'll do is set our mesh in here, and I'll just hide it in Rhino. And I'll just turn off the mesh edges for now. And we'll want to get the mesh to volume component from Dendro. Mesh to volume. And we'll put our mesh in. And we'll get the volume settings component. And there's it has its own parameters too, so you can use even like a volume settings parameter if you just want to keep things organized. So that's going to be our volume settings parameter, and then we need the volume settings component, which is why am I not seeing it here? Sorry, it's called create settings. Okay, so you have your create settings. Okay, so we'll plug that in. And basically what it did is it turned our mesh into a Dendro volume. And the settings have two sets of settings, and in my opinion, it's a little confusing because they're in the same component. Maybe it could have been separate, but so bandwidth and voxel size are settings for creating the volume, and then there's ISO value and adaptivity, which is for creating back to a mesh from the volume. Okay, so if we go now volume to mesh, so volume is a Dendro specific object type. You can even see if you go here, and it's called Dendro volume. It can't be used for anything else except for the Dendro components for here. I think it can be used for transforms as well, but we're not going to be transforming anything. So we'll put the V into volume, and then we use the same settings for going back to a mesh. So mesh to volume is to get it recognized as a Dendro object, and then we're going to go back. We're going to convert that Dendro object back to a mesh. And it's going to create like a shelling. Okay. So, and just to keep in mind, depending on the fidelity that you want of this model and the accuracy, shelling can take some time, but hopefully, even if it's, I don't know, say an hour, it's still better than doing it manually. So first we'll set the settings for the volume to mesh. So we'll get a voxel size. A voxel size is basically like the smaller the size, the more accurate you're going to follow your intended geometry, right? So that's going to create the voxel space. So now every voxel that you don't, I mean, it's behind the scenes, but the voxel grid is basically 0.2, and I'm in millimeters, right? So it's like 0.2 mm. Depending on the units you're using in Rhino and the size of your actual geometry, all these settings that I'm doing now will probably need to be adjusted. And then bandwidth is just the it's just the just like an additional volume offset. So like the lower a bandwidth is, will result in like a quicker computation, but it will have like less adaptability to our original shape. Okay, so again, these are all things that like you have to like experiment with. There's no number that works for every case. You just have to experiment with it. So again, like the higher the bandwidth, the more accurate it will be adaptive wise. The less bandwidth, the more like kind of blocky it will be in terms of adapting to the shape from the pixel grid. Okay, and now we have, so that's the settings for the mesh to volume, and then these two settings are going to then, how do we convert that volume back to a mesh? Okay, so we have an ISO value, and so the ISO value is it's these have to work for closed meshes, and it's kind of like radius based crossing point. Here it says crossing point of volume that is considered the surface. It's just about how closely it will follow our mesh. So in this case, I can use like a pretty small number, 0.002, let's say. 0.002. And I'm actually going to just turn that off, just so that we can get these in without freezing every time. And then adaptivity is going to be a value range from 0 to 1. Like higher adaptivity will allow more variation in polygon size, resulting in fewer polygons, right? So adaptivity is like the resulting mesh, the faces, how similar the size of the faces are. So if you have a higher number, it will allow more variation in the polygon sizes. So that could be good for like really curved things because you can get smaller faces at the curves, bigger faces in the more straight parts. Whereas if you were at 0, everything would try to be the same size as the ISO, which may look kind of blocky and jagged on your curvature. And again, 0 to 1. We'll just start with like something like, I don't know, 0.11. I don't know, just pick a number. Like Dendro is one of those things where like you got to just like start somewhere and then like adjust things until it works. And then so the volume settings we're going to plug into the mesh to volume, right? So again, these two here are controlling this. And then these two here are controlling this. Okay, so what we'll do is turn this on and we'll wait a bit and hope that it goes through. You'll usually end up, really just depends. Oh, so it was not so bad. 2.3 seconds, could have been a lot worse. So if we go down here now and look at this mesh, you'll see down there, if I go and bake this out, and I'll just unpreview. Oddly, it was flipped. So that's the mesh output, right? And that was the adaptivity, right? It's not even that high, and we were still able to get like pretty adaptive in the corners here. So it's a little jaggedy. If I go higher, it's going to take a longer time to compute, longer than I'm willing to wait for this webinar. But if you want to, you should try it out. So you can see all these little faces at the edges where there's bigger pieces that we can span. There's bigger mesh faces, and and all the stuff in between. But the important thing is like, so if I go to rendered, right? The important thing is that you try to get it as close as possible to your intended geometry, and it also depends on the scale you're printing it. Like if you're printing this at ring scale, this is acceptable in resolution of printing. But if it was something bigger, like a big couture necklace or something, like you might see that kind of stuff in the print, and you would have to adjust these settings to be like a bigger adaptivity, maybe a smaller voxel size, and all that would make things calculate for a longer time. If you look down here, we lost some of the fidelity. So if I just do a show, actually, I want to move this. Oops, that was the wrong thing. Didn't want to move that. I just want to move it back, not rotate it. And show. So here was our original with all those intersections, and here's the one from Dendro. So if you adjusted those settings, you'll lose a little bit, but if you adjusted those settings, you could get more and more of that back. Okay, those lines. But again, depending on the scale, it could be acceptable for you. And then there's some like triangulation again, because maybe if we went like a smaller size, but it would just take longer than I want to wait for this video. Okay, and then so this is now a shelled object, and even the cool thing is like even like pieces like this that were like intersecting a little bit or maybe not touching enough. If you look at the Dendro model here, you see how Dendro kind of grabbed that and joined that together. So that would make actually easier for the printing as well. So if we go and I shouldn't have moved that one because now it's going to have to calculate this again because I moved it. So let's just wait a second for that to calculate. Okay. So if I bring this over now, so that's kind of like what we're looking for there, right? A enclosed shelled object. And you have a little channel there. That's fine as long as things are not self-intersecting, right? Versus this. So then you can go and send this off to the printer or do any other kind of additional cleanup. I want to try to show one of those cases. Yeah, like see, like this one was like pretty close. Like that would be kind of hard to print also, or at least it would be really a pain to clean any like kind of support structure, how close those are. But if you see with our Dendro settings, we were able to capture that into a shell. And the nice thing is, once you have that, you can always, once it's back to a mesh, you can always like smooth it further or whatever. One thing that I like to do is I like to do a Laplacian smoothing from Weaverbird. And this can sometimes just, it doesn't add more faces, it's like more like averaging of vertices. This can sometimes get rid of like some of the little jaggedy areas. So I'll just bake that. Bring that over here. So you can see if I bring so that was with the smoothing, and if I turn off the smooth, if I do it, bake it previous, like before smoothing, just hide this clipping plane real quick, just put it over there or something. So if we look at this one, this is before, damn thing, this is before the smoothing, so you can see a little bit more jagged there, whereas after the smoothing, it's still a bit jaggedy, but it does seem a bit less. And you can go even more and more levels. Again, all this stuff, it just, depending on what you do, it will just take more time to calculate. So the other thing I wanted to show you is if we just take the ZBrush way, is just take so I'll just save that. So if we just export this, so I'll get rid of these Dendro ones. So I'll just file, export selected, and export it as an OBJ. And I'll just say, whatever, test. Important is in your options for OBJ, make sure to go to mesh, because for some reason it's on by default, and turn off Ngon, create Ngons. Turn that off, because other softwares, especially like ZBrush, they can't really, like Maya can, but ZBrush not, understand Ngons, and honestly the automatic Ngon creation can mess up your topology when it starts to combine faces. So I just turn it off. It is on by default, so just turn that off. Yeah, and then just go to the desktop. Let's say we'll just call it test. Okay, polygon mesh OBJ. Okay, and then we'll open up ZBrush here, and we'll go to import desktop, get test OBJ, and then you just left click and drag to bring into ZBrush. Make sure you click edit up here. Okay, so now we have our thing here in ZBrush. And what we're going to use is we're going to use a Dynamesh because it's really good at creating these kind of shells. So just so I can show you, like if I smooth this, let's just as a test, if I start to smooth this, you see it starts to kind of like unwrap, and that's because those things were fattened enough that they're self-intersection, as we know from the Rhino. So what I do is I just go to geometry, Dynamesh, and you just play with the resolution until you get like get what you're looking for. So I'll go to like 600, enter, and I'll just click Dynamesh, and that was pretty quick, right? So you see how much quicker that was than Dendro. And if we zoom in, you'll see that like if I smooth this, it's all like it's one enclosed shell, just like Dendro did. Okay. So it's like just much quicker and more robust in ZBrush, and it does the same thing. Like if I look over up in these areas here, you can see that it connected all that stuff up there the same way it did with Dendro. and I'll just go back one. And you know, if you play with the resolution, like if you went like lower, I don't know, like I don't know, 50, or and then the Dynamesh, you see you get something like that, right? Because now your size is bigger, which could be cool. Maybe that's like an effect you're looking for. But yeah, you want to try to get as close as possible. And also you can, if you divide it, like I'll just divide this one time here to give it more faces, and you can actually see when I do that, you can see those lines there. Like if I divide, um, turn on the frame there. So there's the frame there. If I just divide it, oh, it looks the same. It just got more faces, more divisions. It looks smoother. The more divided it is, you can see your points here. So this is 437,580 points. Then the more adaptive the Dynamesh can be. So we can go again to like 300. I don't know. Try. It's going to ask you, would you like to freeze? You just click yes because you want to work on the subdivision level you're working on. Because if you're when you divide stuff here, like if I divide this, oh, it worked actually without it, which is fine, but that's not the point. So when I divide this in ZBrush, you now have a slider that you can slide between the different divisions, and we want to go with our highest. Oh, that's too high. With the division we want. So when you do the resolution, Dynamesh, it's just going to say, would you like to freeze subdivision levels before entering? And you just click yes. So it's going to like get rid of the lower levels, and it's going to Dynamesh the higher level that you're using of divisions. Because it keeps track of, so now see it says freeze subdivision level, and you can't slide that anymore. ZBrush keeps track of those kind of parametrically, so if you divide something, you can always kind of go back. So we'll just do Dynamesh, and you see how like that was really quick at 300. Maybe you want to smooth that out, so it's something like that. Maybe it just like disappears. Or you just go to a higher, you just go to an even higher amount. So like 600, enter Dynamesh, yes, then Dynamesh. Yes, we'll just delete the lower for now, and then Dynamesh. So yeah, so it Dynameshed it there, and you still have the features there. Let's see if we, and then we can go even higher. Let's say, I don't know, let's go to 900. It's gonna take longer. So there's like a orange status bar up there you see sometimes. So that took longer, but still like no time at all. And now we actually kept those features that Dendro didn't keep in such a short time. And the nice thing of ZBrush is you can then just give this like another division. So just divide it again, and you can give it like a nice. If I just increase the draw size here, you can give it a nice like smooth over. And if you have the high face count, you won't like lose a lot of the features. So I just like see I'm like smoothing. See, you can see it getting like blurrier, but you're still keeping the features like here, right? Again, if your purpose is just rendering, then none of this is necessary. You can just render the one from Rhino with the intersections. It doesn't matter. But for production, you'll want to do something like this. And then once you're done with ZBrush, with that, you can just export it. as a new one, I would just say, I don't know, test shell, desktop, save. So ZBrush will just save it. Still saving. It has a lot of faces, so every command you do in ZBrush, there's like this yellow status bar along the top. So right now it's writing obj, and then once this status bar, it's a lot. This is 5.791 million vertices. It's a lot of vertices, and ZBrush handles it pretty well. So again, it's just like finding the right tool for the job. You don't need to always do everything in one software. And then yeah, and then finally, you can go into something like Keyshot, and you can import either one, your shell or your one without the shell. You can take the shell one in. Again, it's just taking some time because it is a lot of vertices, that shelled one. But the important thing is that it doesn't have the self-intersections so that we can print it. Okay, so there's our geometry there in Keyshot, and yeah, and then you can use, you can just, I don't know, go to a material, I don't know, metal. Keyshot's very easy too. You just go to the material and just drag it onto the model. So if we go down and look at just zoom in here. Just want to look at this area here. So yeah, so there's the the result of our shelling at that resolution. Again, as I said before, you can always do like much more resolution. It's just the more time you'll wait. Although in ZBrush you'll wait a lot less time than in anything in Grasshopper that does this kind of thing. So that's the end of our webinar. I hope that you enjoyed it and learned some fun stuff, and just yeah, just have fun playing with like different cell types and making your own cell types. Don't be afraid to do workflows that are both manual and parametric, and don't be afraid to work between different softwares to get done what you're trying to achieve. And I look forward to the live session and hearing your questions. Thank you.